Hello there, and welcome to Life Beyond Seen, where curiosity settles in comfortably and science is explored at a slower, more relaxed pace. This is a place for calm exploration, for letting ideas unfold without rush, and for looking at the natural world in a way that feels steady rather than overwhelming. Tonight's quiet journey turns towards something large, ancient, and surprisingly connected to one of the coldest places on Earth. Not the Antarctica we picture today with endless ice, deep silence, and temperatures that discourage even the most enthusiastic beach plans, but an earlier version of that southern world, one that may once have hosted a visitor famous for its size and reputation. That visitor, according to some lines of scientific evidence, might have been the enormous prehistoric shark known as Megalodon. Now, Megalodon is one of those creatures that tends to arrive with a bit of drama attached. Popular documentaries sometimes give it glowing eyes, loud music, and an attitude problem. The scientific reality is calmer but still fascinating. It lived millions of years ago, long before modern humans appeared. It reached sizes that make even the largest living shark seem modest by comparison. Estimates vary, but many researchers place adult Megalodon somewhere between 15 and 20 metres long, with jaws wide enough to comfortably fit a modern refrigerator, though thankfully without any interest in household appliances. Antarctica, on the other hand, feels like the exact opposite kind of place. Cold, remote, heavily iced over, home mostly to animals adapted to freezing conditions. Penguins, seals, whales passing through cold waters. Not exactly the sort of environment where you would expect a gigantic warm water shark to spend time. And yet, bits of geological evidence, fossil discoveries, climate reconstructions, and oceanographic models suggest that at certain points in Earth's history, conditions were very different. Warm currents moved differently. Continental positions shifted slowly. Sea temperatures near the southern pole were far milder than today. That combination raises an interesting scientific question. Could Megalodon have ranged much farther south than most people assume? Before going deeper into that, let me pause for a moment in the way we usually do here. Wherever you happen to be listening from tonight, whether it is late evening, early morning, or somewhere in the middle of a busy afternoon, I hope you're comfortable. Maybe you're winding down after a long day, maybe you're simply curious, or maybe you just enjoy letting calm, scientific stories play in the background. It is always interesting to picture listeners spread across different time zones, each person arriving at this same moment from a different daily rhythm. If you feel like sharing where you're listening from and roughly what time it is there, it adds a small human layer to these long journeys through science. Something grounding while we talk about oceans that existed millions of years before clocks, calendars, or late-night scrolling. And if you find this style of slower exploration helpful or simply pleasant, a quiet reminder that liking the video or subscribing helps this calm corner reach more people who prefer science without urgency. No pressure, of course. Consider it more like leaving a light on for someone else who might wander in later looking for a gentle explanation rather than a loud one. So, settling back into the topic, the connection between Megalodon and Antarctica isn't built on a single dramatic discovery. There is no complete Megalodon skeleton sitting on Antarctic ice. No dramatic expedition photo with a paleontologist holding up a massive tooth against a penguin backdrop. Instead, the story forms from multiple smaller pieces of evidence. Fossil teeth found in southern ocean regions, geological layers indicating warmer prehistoric climates, shifting continental arrangements that changed ocean currents, chemical signatures in fossils that hint at water temperatures where those animals once lived. Teeth are particularly important here. Sharks, including Megalodon, rarely leave full skeletons behind. Their bodies are mostly cartilage, which does not fossilize easily. Teeth, however, are mineral-rich and durable. Sharks shed thousands of teeth during their lifetimes. Those teeth settle into sediments, sometimes becoming fossils that survive for millions of years. For paleontologists, a fossilized shark tooth is not just a remnant of feeding. It becomes a record of presence, a quiet statement that at some point in some ancient ocean that species passed through. Some Megalodon teeth have been discovered in southern hemisphere sites that push the boundaries of what was once assumed about its habitat. Locations in southern South America, parts of New Zealand, southern Australia, and regions once connected through ancient ocean circulation patterns. These discoveries do not automatically prove Megalodon cruised directly beneath what is now Antarctic ice, but they do widen the map. They suggest a species capable of extensive migration, possibly following prey, temperature zones, or seasonal currents. Temperature is a major factor. Today's Antarctic waters are cold enough to discourage most large warm water predators. But climate reconstructions of the Miocene and Pliocene epochs, when Megalodon lived, indicate significantly warmer global temperatures. Ice sheets were smaller or absent at certain intervals. Ocean heat distribution differed. Warm currents may have extended farther south, carrying both heat and food sources into areas that are now icy. When scientists analyse oxygen isotope ratios in marine fossils, they can estimate past water temperatures. This method, while complex, has provided evidence that southern oceans were once warm enough to support ecosystems very different from what we see now. Large marine mammals lived there. Diverse fish populations existed. Conditions may have been suitable for apex predators like Megalodon, at least seasonally. There is also plate tectonics to consider. Continents move slowly over geological time. Antarctica itself did not always sit in the same climatic isolation it occupies today. The opening and closing of ocean gateways, like the Drake Passage between South America and Antarctica, influenced how cold circumpolar currents formed. Before certain tectonic changes, warmer water exchange between oceans could reach southern latitudes more easily. From a behavioural standpoint, comparisons with modern sharks offer clues. Species such as great white sharks demonstrate impressive migratory behaviour. They travel thousands of kilometres, sometimes crossing entire ocean basins. They follow prey, breeding cycles, or temperature gradients. If a modern shark can do that at 6 meters long, a 20-meter prehistoric relative likely had comparable or greater mobility, assuming similar biological capabilities. That does not mean Megalodon preferred cold water. Most evidence suggests it favoured warmer regions, but preference does not equal strict limitation. Seasonal migration into cooler zones, particularly when prey concentrations increased, remains a reasonable hypothesis. Marine ecosystems often revolve around food availability. If whales, seals, or large fish gathered in southern waters during certain periods, a top predator might follow. Another interesting piece involves associated fossil assemblages. In some southern marine deposits, Megalodon teeth appear alongside fossils of whales and other marine mammals known to inhabit cooler waters. That coexistence hints at overlapping ecological ranges. Not definitive proof of Antarctic residency, but a supporting thread in the larger scientific tapestry. Modern technology continues refining these interpretations. Improved dating methods help determine when fossils formed more precisely. Chemical analyses reveal subtle environmental signals locked within fossilized enamel. Deep-sea exploration occasionally uncovers sediments untouched for millions of years, expanding the fossil record gradually. Despite all this, uncertainty remains. Fossil records are incomplete by nature. Preservation conditions vary widely. Some areas remain unexplored due to logistical challenges, especially around Antarctica, where ice coverage, extreme weather, and remote location complicate research efforts. Absence of evidence does not equal evidence of absence, but it also does not confirm presence. Science moves cautiously in these situations, balancing curiosity with careful interpretation. That cautious approach is part of what makes the topic engaging rather than frustrating. Instead of a single dramatic conclusion, there is an ongoing process. Each new fossil, each refined climate model, each oceanographic simulation adds a small piece. Over time, patterns emerge. Some ideas gain stronger support, others fade quietly. Imagining prehistoric southern oceans also helps frame the discussion. Picture waters without permanent ice sheets, milder temperatures, abundant marine life. Not tropical exactly, but not the frozen environment we associate with Antarctica today. In such a setting, a large migratory shark becomes less implausible. Still impressive, certainly, but not outside ecological possibility. And of course, our own expectations sometimes shape how surprising these findings feel. We often project present-day conditions backward, assuming ancient Earth resembled today's geography and climate. In reality, the planet has gone through dramatic shifts repeatedly. Ice ages, warm periods, continental rearrangements, sea level fluctuations. Oceans we think of as permanently cold have not always been that way. That broader context makes Megalodon's potential southern excursions part of a larger narrative about Earth's dynamic systems. Climate, geology, biology, and oceanography all intersect. A shark tooth in a southern sediment layer becomes a small data point within a planetary story spanning millions of years. As this exploration continues, the next step involves looking more closely at the shark itself. Understanding what Megalodon was biologically, how it lived, what it ate, and how it compared with modern sharks provides important groundwork. Those biological details influence how plausible southern migrations might have been. Size, metabolism, prey preference, reproductive strategies. Each factor contributes to the overall picture, and once those characteristics come into focus, the environmental backdrop becomes clearer as well. Warmer prehistoric oceans, shifting currents, evolving marine ecosystems. All of it ties together gradually, not as a dramatic reveal, but as a steady accumulation of evidence that helps clarify whether that enormous shark might, at least occasionally, have ventured toward the far southern seas where ice now dominates. If we stay with that idea for a moment, the next logical step is simply getting better acquainted with the animal itself. Before thinking about distant southern oceans, climate shifts, or fossil clues scattered across hemispheres, it helps to understand what Megalodon actually was, how it lived, and why it continues to attract attention long after its disappearance. Familiarity with the creature grounds the discussion. Without that foundation, any speculation about where it might have travelled risks floating a bit too far from what biology realistically allows. Megalodon, formerly known as Otodus megalodon, lived roughly between 23 million and 3.6 million years ago, spanning much of the Miocene and Pliocene epochs. That timeline alone is worth pausing over. Humanity, as we recognise it today, did not exist during most of that period. Early hominin ancestors appeared only toward the very end of Megalodon's reign. So when this shark swam through ancient oceans, it did so in a world without human observers, without ships, without coastal cities, without anything resembling modern marine activity. Just oceans, coastlines shaped differently than today, and ecosystems that functioned according to long natural rhythms. Size is often the first detail people mention, and reasonably so. Estimates vary because no complete Megalodon skeleton has ever been found. Sharks are mostly cartilage, which rarely fossilizes. Researchers reconstruct size using tooth dimensions, vertebral fragments, comparisons with living sharks, and biomechanical modelling. Current widely accepted estimates suggest lengths between about 15 and 20 metres, with some researchers cautiously allowing slightly larger possibilities. Weight estimates range from roughly 50 to possibly 70 tonnes. That places Megalodon comfortably among the largest predatory fish ever known. Those numbers can sound abstract, so a few grounded comparisons help. A large great white shark might reach 6 metres. A typical city bus is around 12 metres long. Some modern sperm whales, themselves impressive animals, overlap with Megalodon in size, though they belong to an entirely different lineage. Imagining a shark roughly equivalent to a bus, sometimes longer, moving through water with efficient muscular motion, gives a more practical sense of scale than dramatic exaggerations. Teeth remain the most common fossil evidence, They're triangular, serrated, thick, and robust. Some reach over 18 centimetres in height. Their shape indicates specialisation for cutting through large, dense prey tissue, including bone. Bite force estimates derived from jaw reconstructions suggest one of the strongest bites in vertebrate history, potentially exceeding 100,000 newtons. That sounds technical, but essentially it means the shark could exert enough pressure to fracture large bones, including those of marine mammals. Dietary evidence supports this. Fossil whale bones bearing characteristic bite marks appear in multiple Miocene and Pliocene deposits. The spacing, depth, and shape of these marks match Megalodon tooth morphology. Some whale fossils even show healed bite injuries, indicating encounters where prey escaped but survived. That suggests active predation rather than simple scavenging, although opportunistic feeding likely occurred as well, just as it does with modern sharks. Understanding its prey is relevant when considering geographic range. Large marine mammals migrate widely. Many whale species travel thousands of kilometres annually between feeding and breeding grounds. A predator specialising in such prey might develop similar migratory patterns, following food availability rather than staying confined to a single narrow region. That behavioural flexibility could explain fossil distributions across multiple continents. Metabolism is another factor scientists discuss. Whether Megalodon maintained some level of regional endothermy, partial internal temperature regulation like certain modern sharks, remains debated. Species such as great whites and mako sharks can keep parts of their bodies warmer than surrounding water. This adaptation improves swimming efficiency, hunting capability, and tolerance of cooler waters. If Megalodon shared similar physiology, it would broaden the range of environments it could comfortably enter. Swimming efficiency itself matters too. Large body size in aquatic animals often supports long-distance travel. Whales demonstrate this clearly. Hydrodynamic modelling of Megalodon suggests a powerful tail structure capable of sustained cruising speeds. Not necessarily constant rapid pursuit, but efficient, steady movement suitable for migration. That would allow seasonal travel between warmer core habitats and cooler peripheral zones when ecological conditions encouraged it. Reproduction remains less well understood, but nursery area hypotheses exist. Some fossil sites containing numerous smaller Megalodon teeth suggest coastal nursery grounds, where juveniles developed in relatively sheltered environments. Modern sharks use similar strategies. If true, that indicates at least some degree of habitat specialization depending on life stage. Adults may have ranged widely, while younger individuals stayed closer to warmer coastal regions offering protection and food. Extinction discussions also intersect with geographic range. Megalodon disappeared around 3.6 million years ago, roughly coinciding with global cooling trends, changes in sea levels, shifting marine mammal populations, and possible competition from emerging predators like early great white sharks. Cooling oceans would reduce suitable habitat if the species preferred warmer waters. That decline hints indirectly at earlier flexibility. Species that once ranged widely may become restricted as environmental conditions change. Looking at global fossil distribution reinforces that sense of wide reach. Megalodon teeth appear on every continent except Antarctica itself, though offshore southern deposits complicate the picture. North America, South America, Europe, Africa, Asia, and Australia all produce finds. Some sites lie in what were once warm, shallow seas. Others suggest deeper offshore habitats. The overall pattern indicates a cosmopolitan marine predator, rather than a regionally isolated species. Oceanography during the Miocene and Pliocene also differed significantly. Warmer global temperatures reduced polar ice extent. Sea levels were often higher. Continental arrangements allowed different current patterns. Warm equatorial waters circulated differently, sometimes reaching higher latitudes than today. That background environment forms the stage on which Megalodon lived. Without understanding that stage, interpreting fossil locations becomes harder. An additional detail involves isotopic analysis of tooth enamel. Ratios of oxygen isotopes can reflect water temperature at the time the enamel formed. Some Megalodon teeth show values consistent with cooler waters than traditionally assumed, though interpretation requires caution because physiology, migration, and local conditions complicate readings. Still, these data points contribute to the ongoing discussion about habitat tolerance. Behaviourally, Megalodon likely resembled large modern predatory sharks in certain respects. Solitary hunting interspersed with occasional aggregation around abundant prey sources seems plausible. Marine predators often converge temporarily where food is plentiful, such as whale migration corridors or productive upwelling zones. Such temporary congregation does not imply permanent residence, but does expand effective range. It is also worth mentioning sensory capabilities. Sharks possess highly developed electroreception through ampullae of Lorenzini, allowing detection of tiny electrical signals from prey. They also rely on acute olfactory senses and low-frequency vibration detection. These sensory adaptations function across a wide range of marine environments, from tropical shallows to deeper, cooler waters, provided physiological tolerance exists. Some earlier depictions presented Megalodon as strictly tropical, but more recent analyses soften that view. Many large marine animals display broader temperature tolerances than once assumed. Ecological plasticity often enhances survival. Strict specialization, while advantageous in stable conditions, can become risky during environmental change. Megalodon's long temporal span suggests it navigated multiple climatic phases successfully before eventual extinction. From a structural perspective, jaw mechanics offer additional clues. Modelling indicates a wide gape, robust musculature, and teeth arranged for both slicing and crushing. That versatility supports a diet including large whales, smaller marine mammals, sizable fish, and possibly carrion. A varied diet typically correlates with broader geographic distribution, again reinforcing the plausibility of occasional excursions beyond core warm zones. One point sometimes overlooked involves predator-prey dynamics. Apex predators influence ecosystems through top-down control. Their presence shapes prey behaviour, distribution, and evolutionary pressures. If Megalodon occasionally entered cooler southern waters, even seasonally, its ecological impact could extend beyond permanent residence, influencing marine community structure indirectly. Fossil record gaps complicate firm conclusions. Antarctica's thick ice cover limits accessible sediment exposure. Offshore drilling projects occasionally recover marine sediments, but logistical challenges remain significant. Future discoveries could clarify the picture, either strengthening or weakening the hypothesis of southern Megalodon presence. Technological improvements continue aiding this research. Remote sensing, improved dating techniques, microfossil analysis, and refined climate modelling all contribute incremental insights. None provide instant answers, but together they gradually refine understanding of ancient marine ecosystems. Public fascination with Megalodon sometimes focuses on dramatic imagery rather than scientific nuance. Stories of surviving individuals in modern oceans persist despite lack of credible evidence. From a scientific standpoint, extinction around 3.6 million years ago remains strongly supported. Still, the interest reflects something broader. Humans remain intrigued by large, powerful animals, especially those that once dominated environments we still depend on. Studying Megalodon also informs modern marine biology. Understanding how apex predators respond to climate change, prey shifts, and habitat alterations offers perspective on current ocean ecosystems. The past provides case studies, not direct predictions, but useful analogies. Antarctica, meanwhile, continues evolving. Ice sheets fluctuate over geological time. Ocean currents shift. Marine ecosystems adapt. The southern oceans today differ from those Megalodon knew, but they are part of the same long planetary story. That continuity helps explain why scientists examine fossil clues so carefully. Each tooth, Each sediment layer, each isotopic signature adds context. So, with a clearer sense of what Megalodon was biologically, how it likely behaved, and how widely it already ranged across ancient oceans, attention naturally moves toward environmental conditions farther south. Warmer prehistoric Antarctica, shifting currents, available prey populations, and geological evidence begin fitting into the broader picture. Understanding the shark itself makes evaluating those southern clues more grounded, less speculative, and increasingly connected to the larger patterns shaping Earth's oceans over millions of years. When thinking about whether a giant prehistoric shark could ever have moved through southern polar waters, the environment itself becomes just as important as the animal. Antarctica today is defined by ice, wind, and temperatures that rarely encourage extended marine vacations. Thick continental ice sheets dominate the landmass, and cold circumpolar currents isolate the region from warmer oceans. That picture feels permanent because it is all humanity has ever known. Yet geological evidence makes it very clear that Antarctica has not always looked or behaved this way. Long before extensive ice coverage formed, the southern polar region supported conditions that were milder, wetter, and biologically active in ways that can feel surprising at first glance. Going back tens of millions of years helps reset expectations. During much of the early Cenozoic era, particularly the Paleocene and Eocene epochs, roughly 66 to 34 million years ago, Earth experienced significantly warmer global climates than today. Atmospheric carbon dioxide concentrations were higher, polar temperature gradients were smaller, and permanent ice sheets had not yet formed in the way they later would. Antarctica, positioned over the South Pole even then, still experienced seasonal darkness and light cycles, but temperatures were far less extreme. Geological cores extracted from Antarctic sediments show evidence of forests, freshwater systems, and diverse marine ecosystems. Fossilized plant material discovered on the continent provides some of the most direct confirmation. Leaves, pollen grains, wood fragments, and root structures preserved in sedimentary rock layers indicate the presence of temperate forests. These were not tropical jungles, but they were environments capable of supporting trees similar to southern beech, along with ferns and various understory plants. Such vegetation requires liquid water, moderate temperatures, and seasonal stability. The existence of those forests immediately signals a climate very different from modern Antarctic conditions. Marine evidence aligns with this picture. Fossils of mollusks, fish, marine reptiles from earlier periods, and later marine mammals show that surrounding seas hosted productive ecosystems. Water temperatures reconstructed through oxygen, isotope analysis of shells and microfossils suggest conditions that, while cool compared with equatorial oceans, were not inhospitable. Estimates vary by epoch, but some coastal waters may have ranged between roughly 10 and 18 degrees Celsius during warmer intervals. That temperature range comfortably supports diverse marine life today in many parts of the world. Tectonic processes played a major role in shaping this ancient environment. Antarctica was once connected to other southern landmasses as part of the supercontinent Gondwana. Over tens of millions of years, continental drift separated Antarctica from Australia, South America, and Africa. These separations gradually altered ocean circulation patterns. Before certain ocean gateways opened fully, warm equatorial currents could flow southward more freely. Heat distribution across the planet followed different pathways than it does today. One particularly influential development involved the opening of the Drake Passage between South America and Antarctica, along with the Tasman Gateway between Antarctica and Australia. As these passages widened, they allowed the formation of the Antarctic Circumpolar Current, a powerful ring of cold water that now circles the continent. This current effectively thermally isolates Antarctica, limiting the influx of warmer waters. Before its establishment, ocean mixing was less restricted. Warmer currents could reach higher southern latitudes, moderating regional climate. Timing matters here. Megalodon lived primarily between about 23 million and 3.6 million years ago. By that point, Antarctic glaciation had begun, but the extent and stability of ice sheets fluctuated. Climate records show cycles of warming and cooling, with some intervals featuring reduced ice volume and relatively warmer ocean conditions compared with today. The Miocene climatic optimum, around 17 to 14 million years ago, represents one such warmer phase. Global temperatures rose, sea levels increased, and marine ecosystems adjusted accordingly. Sea level changes during these periods also reshaped coastlines. Higher sea levels submerged continental shelves, creating extensive shallow marine habitats. Such environments often support rich food webs, including plankton blooms, fish populations, and marine mammals. For large predators, expanded coastal and offshore feeding grounds would provide strong incentives for migration. The southern oceans during warmer intervals likely offered seasonal concentrations of prey. Marine mammal evolution intersects directly with this story. The Miocene saw diversification of baleen whales, toothed whales, seals, and other marine mammals. Fossils from southern hemisphere deposits indicate their presence in regions closer to Antarctica than modern distributions might suggest. Large whales, in particular, represent significant caloric resources for apex predators. If whales migrated into southern feeding grounds following plankton productivity, predators specialized in hunting them could reasonably follow. Ocean productivity depends heavily on nutrient circulation. Upwelling zones where deep, nutrient-rich waters rise toward the surface stimulate plankton growth. These plankton blooms support fish populations, which in turn support marine mammals. Geological evidence suggests ancient upwelling patterns in southern oceans that differed from modern configurations. Changes in wind patterns, continental positions, and ocean gateway geometry all influence these systems. Temperature tolerance in marine animals varies widely. Some species strictly require warm water, others operate effectively across broader ranges, especially if they possess physiological mechanisms for maintaining internal body temperature above ambient conditions. Certain modern sharks demonstrate regional endothermy, retaining metabolic heat in swimming muscles and critical organs. If Megalodon possessed similar adaptations, cooler southern waters would not necessarily prevent temporary habitation. Sedimentary evidence collected through ocean drilling programs provides additional clues. Layers of microfossils, chemical signatures, and mineral compositions help reconstruct ancient ocean temperatures, salinity levels, and circulation patterns. These records consistently indicate dynamic climate fluctuations rather than a single stable Antarctic condition. Periods of reduced ice, warmer sea surface temperatures, and active marine ecosystems appear repeatedly across geological timelines. Antarctica's terrestrial environment also transitioned gradually. Forested landscapes gave way to tundra-like conditions before large-scale glaciation dominated. That transition influenced freshwater runoff, sediment delivery to coastal zones, and nutrient input into adjacent seas. Coastal productivity often increases when terrestrial ecosystems supply organic material to marine environments. This link between land and sea further supports the idea of biologically active southern oceans during warmer intervals. Evidence from fossil fish species strengthens the reconstruction. Certain fish assemblages found in southern deposits resemble communities currently associated with temperate rather than polar climates. Their anatomical features, growth patterns, and isotopic signatures align with moderate water temperatures. Since fish form foundational links in marine food chains, their presence implies broader ecological viability. Ice sheet formation itself was not instantaneous. Geological data indicates cycles of expansion and retreat influenced by orbital variations, atmospheric greenhouse gas levels, and ocean heat transport. Even after initial Antarctic glaciation began around 34 million years ago, significant variability persisted. Some intervals likely featured reduced ice coverage, especially along coastal margins, opening access to productive marine habitats. Wind patterns around Antarctica also evolved over time. Today's strong circumpolar westerlies help maintain cold isolation. Earlier atmospheric circulation may have been weaker or differently configured, allowing greater mixing between polar and mid-latitude air masses. Atmospheric heat transport contributes alongside ocean currents in determining regional climate. Another important factor involves salinity. Freshwater input from melting ice affects ocean density and circulation. In warmer periods with less permanent ice, salinity patterns would shift. These changes influence nutrient mixing, marine productivity, and habitat suitability for various species. Subtle chemical traces preserved in marine sediments help reconstruct these conditions. Volcanic activity in parts of Antarctica and surrounding regions may also have contributed localized warmth. Subglacial volcanism continues today beneath certain Antarctic ice sheets. In earlier periods with less ice coverage, geothermal influences might have affected coastal ecosystems more directly, though the scale of this effect remains debated. Considering all these elements together creates a picture of Antarctica not as a permanently frozen outlier, but as a region that has experienced substantial environmental variation. Temperate forests, ice-free coastlines, warmer seas, diverse marine life, and shifting ocean connections all appear at different points in its history. This perspective helps remove the immediate sense of improbability when discussing large marine predators near the southern polar region. Still, environmental suitability alone does not confirm Megalodon's presence. Biological capability, prey availability, and fossil evidence must align. Climate reconstruction sets the stage, but direct traces of the animal remain essential. That brings attention back to the fossil record itself. Teeth, sediment associations, isotopic measurements, and geographic distribution patterns form the next layer of investigation. Understanding ancient Antarctica's climate simply provides context. It establishes that the region, during certain intervals, could plausibly support large marine predators. Without that context, any discussion of Megalodon in southern waters would feel immediately unrealistic. With it, the idea becomes a scientific hypothesis subject to evidence rather than a speculative stretch. Research continues to refine temperature estimates, current models, and ecological reconstructions. Each new sediment core, fossil discovery, or analytical technique adds resolution. Antarctica remains difficult to study extensively due to logistical challenges, but gradual accumulation of data continues. From here, attention naturally shifts toward the specific clues that suggest Megalodon's range may indeed have extended farther south than once assumed. Fossil discoveries, distribution patterns, and chemical analyses begin to take centre stage, gradually building a clearer sense of how far this large shark may have travelled through ancient oceans that, at times, looked very different from the cold southern seas familiar today. With that environmental backdrop in mind, attention naturally turns toward the physical traces left behind. Climate models, tectonic reconstructions, and ocean current simulations can suggest possibilities, but fossils provide something more tangible. They are not dramatic answers carved neatly into stone. Usually they appear as isolated finds, fragments, scattered clues that only begin to make sense when viewed collectively over many years of research. In the case of Megalodon and southern oceans, the story starts quietly with teeth turning up in places that once seemed farther south than expected for a large warm water shark. Teeth dominate the Megalodon fossil record for very practical reasons. Sharks constantly shed teeth throughout their lives. Each tooth, once lost, sinks into seabed sediment. Over time, mineralization can preserve it. Because Megalodon was both large and long-lived as a species, it likely produced an enormous number of teeth across millions of years. Even so, the fossil record is uneven. Some regions preserve remains well, while others erase them entirely through erosion, tectonic recycling, or simple lack of sediment accumulation. That unevenness makes every southern find particularly interesting. Southern Hemisphere discoveries began attracting attention decades ago. Coastal deposits in southern South America produced several Megalodon teeth embedded in marine sediment layers dated to the Miocene and Pliocene epochs. Argentina and Chile in particular yielded specimens that suggested the shark-inhabited waters closer to high southern latitudes than earlier maps had indicated. At first, these finds were treated cautiously. Individual fossils can be transported by currents or reworked into younger sediments. Confirmation requires consistent stratigraphic context, reliable dating, and ideally multiple finds from similar horizons. As additional specimens surfaced, patterns slowly emerged. New Zealand became another significant source. Marine sedimentary formations there, many formed in temperate to cool prehistoric seas, produced Megalodon teeth alongside fossils of whales, seals, and diverse fish species. The associated fauna provided important ecological context. These were not isolated warm lagoons, but open marine environments, influenced by broader ocean circulation. Australia contributed further pieces. Southern coastal deposits yielded teeth comparable in size and morphology to Megalodon finds elsewhere. Some sites showed repeated occurrences across stratigraphic layers, suggesting persistent or recurrent presence rather than a single unusual incursion. Dating techniques, including biostratigraphy using microfossils and radiometric methods, where volcanic ash layers were present, helped narrow the timeframes involved. One key aspect researchers consider is depositional environment. Marine sediments differ depending on depth, proximity to shore and water temperature. By analysing sediment grain size, fossil assemblages and chemical composition, scientists infer whether a fossil formed in shallow coastal water, deeper offshore zones, or transitional shelf environments. Many southern Megalodon teeth appear in sediments consistent with productive continental shelf habitats, areas known for high biological productivity. Continental shelves often serve as feeding grounds for marine mammals. Whales, particularly baleen whales, exploit plankton blooms supported by nutrient upwelling along these margins. That ecological link matters because Megalodon is widely interpreted as a predator of large marine mammals. Finding its teeth in sediments associated with whale fossils strengthens the case for ecological interaction rather than accidental transport. Chemical analysis of tooth enamel provides another layer of information. Oxygen isotope ratios reflect water temperature during enamel formation. While physiological factors complicate interpretation, some southern Megalodon teeth show isotope values consistent with cooler waters than traditional tropical habitat assumptions would predict. Researchers interpret these cautiously, but repeated patterns across multiple sites add weight to the possibility of broader temperature tolerance. Transport processes always require consideration. Ocean currents can carry teeth significant distances after shedding. Storm events, sediment slumping, or river outflows might redeposit fossils far from their original location. To address this, paleontologists examine wear patterns, breakage, and sediment consistency. Well-preserved teeth embedded in undisturbed strata usually indicate local origin rather than long-distance transport. Southern South Africa also enters the discussion. Fossil deposits along the southern African coastline contain Megalodon teeth, within marine assemblages indicating temperate conditions. These finds help bridge geographic gaps between equatorial regions and more southern latitudes, suggesting a gradient rather than an abrupt boundary in the shark's historical range. Ocean drilling programs have occasionally retrieved sediment cores from southern ocean basins. While Megalodon teeth remain rare in such cores, microfossil assemblages from the same layers help reconstruct marine conditions during the shark's era. Warmer sea surface temperatures, productive ecosystems, and migratory marine mammals appear repeatedly in these reconstructions. Whale fossil evidence deserves closer attention because of its indirect implications. Large baleen whale fossils discovered in southern hemisphere Miocene deposits often show bite marks matching Megalodon dentition. The spacing, curvature and serration impressions align with tooth morphology. Some bones show healing, indicating survival after predatory encounters. These traces imply predator-prey interaction in those regions. Seals and smaller marine mammals also appear in southern fossil assemblages from relevant time periods. Although not primary prey compared with whales, their presence contributes to a diversified food web capable of sustaining large predators. Apex predators rarely depend on a single prey species exclusively, especially across wide geographic ranges. Sediment temperature proxies complement fossil evidence. Certain microfossils, like foraminifera, incorporate environmental signals into their shells. Analysis of these shells indicates water temperatures, salinity levels, and nutrient availability. Southern Hemisphere deposits from the Miocene climatic optimum show conditions warmer than present, supporting broader ecological viability. It's important to emphasize that no confirmed Megalodon tooth has been recovered directly from the Antarctic continental landmass itself. Ice coverage and limited exposed sediment complicate access. However, offshore Southern Ocean deposits remain less explored compared with more accessible continental shelves. Future drilling or subglacial sediment studies may alter the current picture. Another interesting clue comes from the size distribution of southern teeth. Some specimens rank among the larger Megalodon teeth globally. Larger individuals often occupy higher trophic positions and possess greater migratory capability. While size alone does not prove southern residency, it supports the idea that mature individuals could travel extensively. Modern analogues provide perspective. Great white sharks, although smaller, migrate across vast distances, including into relatively cool waters off South Africa, southern Australia, and occasionally farther south following prey. Satellite tagging studies show seasonal movements linked to temperature gradients and prey distribution. Extrapolating cautiously, a larger ancestral predator could have exhibited comparable patterns. Seasonality itself becomes relevant. Southern ocean productivity often peaks during certain periods when sunlight returns after polar winter, stimulating plankton growth. That productivity attracts fish, then marine mammals, then predators. A seasonal presence of Megalodon in southern waters aligns with ecological logic, even if year-round residency remains uncertain. Sedimentary dating precision continues improving. Advances in magnetostratigraphy, isotopic calibration, and refined fossil correlation allow tighter age constraints. As dating improves, correlations between climate phases and fossil occurrences become clearer. Some southern Megalodon finds correspond to warmer intervals within broader cooling trends. Public interest sometimes interprets these findings dramatically, but scientific interpretation remains incremental. Each tooth, each associated fossil, each chemical signature contributes to probability rather than certainty. Scientific conclusions rarely hinge on a single piece of evidence. Instead, they accumulate through convergence of multiple independent lines of inquiry. Logistical challenges persist. Antarctic expeditions are expensive, weather-dependent and environmentally regulated. Sampling opportunities remain limited. Marine sediment recovery in polar regions requires specialized vessels and equipment. Despite these obstacles, research continues steadily. Collaborative international programs play a significant role. Shared data repositories, coordinated drilling efforts, and interdisciplinary teams help integrate geological, biological, and chemical perspectives. Understanding ancient marine ecosystems requires that combined expertise. As more southern hemisphere fossils are catalogued and analysed, distribution maps of Megalodon continue adjusting slightly. Early assumptions of strictly tropical distribution have softened toward recognition of broader ecological flexibility. Not unlimited range, but more extensive than once thought. Climate modelling studies complement fossil distribution. Simulations of Miocene ocean temperatures and currents indicate corridors of relatively warm water extending toward higher southern latitudes during certain intervals. These modelled corridors correspond broadly with regions where southern Megalodon teeth have been discovered. Still, uncertainty remains inherent. Fossil preservation biases, sampling gaps, and dating uncertainties all influence interpretation. Scientific caution reflects these limitations rather than reluctance to consider new ideas. Evidence suggesting southern range expansion remains plausible, but not definitive. That measured approach keeps discussion grounded. Instead of imagining dramatic permanent megalodon populations beneath Antarctic ice, researchers focus on probabilities. Occasional migration, seasonal hunting grounds, or peripheral range expansion represent more realistic scenarios consistent with available data. From here, the details of how teeth themselves preserve information become increasingly important. Understanding what fossilized enamel can reveal about temperature, diet, and environment helps interpret those southern discoveries more precisely. The teeth are not just evidence of presence, they function as biological recorders, holding subtle chemical clues about the waters through which their owner once moved. When those fossil teeth begin appearing in the southern deposits, the next step naturally involves asking what exactly they can tell us beyond simple presence. At first glance, a fossilized shark tooth looks like a durable leftover from a feeding event, something that survived while softer tissues disappeared. Yet researchers increasingly treat these teeth less like isolated objects and more like compact environmental archives. Their structure, chemistry, and wear patterns hold information about temperature, diet, habitat conditions, and even aspects of migration. They are not perfect records, but they often provide more detail than people expect. Shark teeth form from highly mineralized tissues, primarily enamel-like enameloid and dentine. These materials resist decay far better than cartilage or soft tissue. Once shed, a tooth can settle into sediment relatively quickly, especially in coastal shelf environments, where deposition rates are higher. Burial protects it from mechanical erosion, scavenging, and chemical dissolution. Over geological time, mineral replacement can strengthen the fossil further, preserving microscopic details. The durability of these tissues is why paleontologists rely heavily on teeth to reconstruct ancient shark biology. Megalodon, constantly replacing teeth throughout its lifetime, produced thousands of them. That abundance increases the statistical reliability of fossil samples compared with animals that shed fewer hard parts. Even so, interpreting teeth requires careful methodology. Misidentification, reworking, or contamination can distort conclusions. One major analytical tool involves stable isotope analysis, particularly oxygen isotopes. Oxygen atoms come in slightly different forms, or isotopes, and the ratio between them in biological tissues often reflects the temperature of the surrounding water during formation. When a megalodon tooth formed, the chemical environment of the shark's body incorporated oxygen from seawater through diet and metabolism. That isotopic signature can persist in fossil enamel millions of years later. Extracting this information involves microscopic sampling and laboratory measurement using mass spectrometry. Researchers compare isotope ratios with established calibration curves derived from modern marine organisms. The result provides an estimate, not an exact temperature reading, but enough to distinguish between tropical, temperate, and cooler water conditions. Southern Hemisphere megalodon teeth sometimes show values indicating cooler waters than previously assumed. Interpretation remains complex because physiology plays a role. If Megalodon possessed partial endothermy, maintaining body temperatures above ambient water, isotopic readings might reflect internal conditions rather than external seawater directly. Scientists account for this by comparing results across multiple specimens and locations. Consistent patterns strengthen confidence in environmental interpretations. Carbon isotopes provide additional dietary clues. Different prey species occupy different positions in marine food webs, and those positions influence carbon isotope ratios. By analysing carbon signatures in tooth enamel, researchers infer whether Megalodon consumed primarily marine mammals, large fish, or mixed diets. Southern specimens often align with diets consistent with marine mammal predation, matching fossil whale distributions in those regions. Trace element analysis extends the toolkit further. Elements such as strontium, magnesium, and barium incorporate into tooth tissues in small amounts. Their concentrations can reflect salinity, water chemistry, and sometimes migration between distinct marine environments. Variations along the growth axis of a tooth may indicate movement between regions with different chemical signatures. Growth patterns within teeth also hold information. Incremental layering occurs during tooth formation, somewhat analogous to growth rings in trees, though more subtle. Advanced imaging techniques, including scanning electron microscopy and synchrotron radiation analysis, reveal microstructural layering. Researchers sometimes correlate these layers with environmental fluctuations or growth rates, where patterns offer behavioral hints. Teeth subjected to repeated bone contact show distinctive microfractures, polish, and serration rounding. Many megalodon teeth display such wear, supporting active predation on large vertebrates rather than exclusive scavenging. Southern teeth with similar wear patterns imply comparable feeding behavior in those regions. Another interesting aspect involves coloration. Fossil tooth color depends largely on surrounding sediment chemistry during fossilization. Darker tones often indicate phosphate-rich marine sediments, while lighter hues may reflect different mineral conditions. While color alone does not indicate temperature or geography, consistent coloration across regional deposits helps confirm local fossilization rather than long-distance transport. Contextual sediment analysis complements tooth chemistry. Researchers examine the matrix surrounding fossils for microfossils, mineral content, and grain size. That context helps reconstruct depositional environment depth, energy conditions, and water chemistry. Teeth found embedded in undisturbed marine shelf sediments carry stronger environmental signals than those in mixed or reworked deposits. Radiometric dating sometimes assists when volcanic ash layers occur near fossil-bearing strata. Techniques like argon-argon dating provide absolute age estimates. Combined with biostratigraphic markers, these methods help place megalodon teeth within precise geological intervals, allowing correlation with known climate phases. Time resolution matters because megalodon existed through periods of significant climate fluctuation. A tooth from a warmer Miocene interval might indicate broader southern range than one from a cooler late Pliocene phase. Accurate dating allows researchers to map habitat changes over time, rather than treating the species as ecologically static. Comparative studies with modern sharks strengthen interpretation frameworks. Researchers analyze isotopic signatures in teeth of living species across known temperature gradients. These modern baselines help calibrate fossil interpretations. Similar patterns observed in fossil teeth suggest comparable ecological responses, though always with caution due to evolutionary differences. Transport bias remains an ongoing consideration. Ocean currents, storms, and sediment flows can move teeth from original habitats. Scientists assess this risk by examining abrasion, breakage, and associated fauna. Intact teeth within consistent marine assemblages strongly suggest local origin rather than distant transport. Juvenile versus adult teeth provide additional nuance. Smaller teeth found in certain regions might indicate nursery areas, while larger teeth suggest adult presence. Some southern hemisphere deposits contain primarily larger specimens, hinting at migratory adults rather than permanent breeding populations. This aligns with seasonal migration hypotheses. Technological advances continue improving resolution. Laser ablation techniques allow sampling along tooth growth axes without destroying entire specimens. Three-dimensional imaging reveals internal structures previously inaccessible. Chemical mapping at microscopic scales uncovers environmental gradients within single teeth. Despite these advances, limitations persist. Diagenesis, the chemical alteration of fossils after burial, can modify original isotopic signals. Researchers apply screening techniques to identify altered samples, but some uncertainty always remains. Multiple independent analyses help mitigate this risk. Collaboration across disciplines strengthens conclusions. Geochemists, paleontologists, oceanographers, and climate modelers combine expertise. Integrating chemical data with ecological modelling produces more robust interpretations than any single method alone. Public interest sometimes focuses on the dramatic size of Megalodon teeth rather than their scientific value. Yet for researchers, a modest fragment analysed carefully can provide more insight than a pristine large specimen lacking contextual data. Scientific interpretation prioritises information content over visual impact. The cumulative effect of these analyses gradually refines understanding. Teeth become more than evidence of existence. They function as environmental recorders, storing subtle clues about ancient oceans. When multiple teeth from southern deposits consistently indicate cooler water conditions, marine mammal diets, and local sediment context, the argument for broader geographic range gains credibility. This does not produce a definitive map with clear boundaries. Marine ecosystems rarely follow neat borders. Instead, the picture resembles a gradient of probability, with core habitats in warmer regions and peripheral excursions into cooler zones when ecological conditions supported them. As analytical techniques continue advancing, previously collected specimens sometimes yield new information. Museums hold extensive collections gathered decades ago. Re-examining those teeth with modern methods occasionally shifts interpretations. The fossil record, in that sense, continues speaking long after initial discovery. Understanding teeth as environmental archives sets the stage for examining broader geological indicators. Sediment layers, continental drift evidence, and ocean circulation models complement biological data. Together, they help clarify whether southern waters merely received occasional Megalodon visitors or supported more regular seasonal presence tied to larger planetary changes. Once the fossil teeth themselves begin offering chemical hints and contextual clues, the next layer of evidence naturally comes from the geological framework surrounding them. Teeth alone can suggest presence, but geology helps explain pathways, environmental continuity, and the broader physical conditions that would have made southern movement possible in the first place. Instead of focusing on a single fossil or location, this approach examines sedimentary patterns, continental motion, ocean basin development, and the structural history of Earth's crust. Those slow geological processes create the routes through which marine species travel, often long before any particular animal actually uses them. Plate tectonics sits at the centre of that framework. Earth's outer shell consists of large moving plates, drifting gradually over millions of years. Continents are not fixed. They shift, collide, separate, and reshape ocean basins. During the Miocene and Pliocene, when Megalodon lived, continental arrangements were similar to today in broad outline but still evolving in detail. The southern hemisphere, in particular, experienced significant adjustments affecting ocean circulation and climate gradients. Antarctica had already separated from Australia and South America by that time, yet the degree of separation and the geometry of the connecting ocean gateways was still changing. The widening of the Drake Passage between South America and Antarctica and the Tasman Gateway between Antarctica and Australia allowed the eventual development of the Antarctic circumpolar current. This current now isolates Antarctica thermally, keeping southern waters cold. Earlier in its development, however, circulation patterns may have permitted greater mixing of warmer waters into southern latitudes. Sediment cores recovered from ocean drilling projects provide tangible records of these changes. Layers of microscopic fossils, mineral grains, and chemical markers accumulate year after year on the seafloor. By extracting cylindrical cores and analysing their stratigraphy, geologists reconstruct environmental conditions stretching back tens of millions of years. These cores reveal fluctuations in ocean temperature, productivity, and circulation strength. Several southern ocean cores show intervals during the Miocene when temperatures were higher than present, aligning with the broader Miocene climatic optimum. Continental shelf development also plays a role. Shelves represent relatively shallow submerged extensions of continents, often biologically productive due to sunlight penetration and nutrient mixing. As sea levels rose during warmer climatic phases, shelves expanded. That expansion created extensive feeding grounds attractive to marine mammals and, by extension, their predators. Geological mapping of ancient shelf deposits in southern regions indicates periods when such habitats extended closer to Antarctic latitudes than they do today. Another geological factor involves sediment transport pathways. Rivers, coastal erosion, and underwater currents move sediments continuously. These processes leave identifiable signatures in rock formations. Grain size distributions, mineral composition, and fossil content allow geologists to trace sediment origins and transport distances. Some southern marine deposits containing Megalodon teeth show minimal evidence of long-distance transport, supporting the interpretation that the animals were present locally, rather than their remains drifting far from northern habitats. Volcanic ash layers occasionally preserved within marine sediments provide valuable chronological markers. When a volcanic eruption spreads ash over wide regions, that layer settles simultaneously across large areas. Radiometric dating of volcanic minerals within the ash establishes precise time references. Correlating fossil-bearing sediment layers with dated ash horizons helps place Megalodon occurrences within specific climatic intervals. Seafloor topography also influences marine migration routes. Submerged ridges, basins, and continental margins affect current flow, nutrient distribution, and habitat accessibility. Geological surveys using sonar mapping have revealed ancient submerged ridges that may have served as ecological stepping stones, supporting chains of marine life extending towards southern latitudes. Such features can concentrate nutrients and prey species, indirectly guiding predator movements. Glacial history intersects with this discussion as well. Antarctic glaciation intensified over time, but it did so gradually. Geological evidence shows cycles of ice advance and retreat, with some intervals featuring reduced ice coverage. During those warmer phases, coastal environments would have been more accessible, potentially supporting richer marine ecosystems. Sediment deposits containing glacial drop stones interlayered with warmer water microfossils illustrate these alternating conditions. Isostatic adjustment adds another dimension. When large ice sheets grow, they depress the underlying crust. When ice retreats, the land rebounds. This vertical movement influences coastal geometry, sea level relative to land, and marine habitat distribution. Geological records indicate repeated cycles of such adjustment in Antarctic regions, affecting shelf exposure and marine accessibility over millions of years. Mineralogical studies of marine sediments reveal shifts in ocean chemistry over time. Ratios of certain elements reflect weathering rates on continents, volcanic activity, and ocean circulation changes. These chemical fingerprints help reconstruct nutrient flow into southern oceans, which in turn affects biological productivity. Productive waters attract prey species, setting the stage for predator presence. Fossilized microplankton assemblages provide especially detailed climate indicators. Species composition of foraminifera, diatoms and coccolithophores shifts predictably with water temperature and nutrient availability. Southern Hemisphere sediment cores containing warm water microplankton species during certain Miocene intervals support the idea of relatively mild marine conditions extending toward higher latitudes. Continental erosion patterns further inform the picture. Mountain building, river systems, and coastal erosion deliver sediments to oceans. Variations in sediment supply affect marine turbidity, nutrient levels, and habitat structure. Geological evidence suggests that southern continental margins experienced active erosion phases that would have enriched nearby marine environments with nutrients. Ocean gateway evolution remains particularly significant. As tectonic separation progressed, the geometry of ocean passages changed gradually rather than abruptly. Partial restrictions, varying depths and shifting sill heights influenced water exchange between basins. Climate models incorporating these gateway changes show periods when warm water intrusion into southern oceans remained plausible before full circumpolar isolation developed. Paleomagnetic studies also contribute. Magnetic minerals within sediments align with Earth's magnetic field at the time of deposition. Reversals in magnetic polarity provide chronological markers that help date sediment layers precisely. Correlating these magnetic signatures with fossil occurrences allows researchers to align Megalodon evidence with known geological timelines. Seismic reflection surveys, commonly used in offshore geological exploration, reveal buried sediment structures without direct drilling. These surveys map sediment thickness, layering patterns, and structural features. In some southern ocean regions, seismic data indicate extensive sediment sequences consistent with long-term stable marine environments during periods when Megalodon existed. Hydrothermal activity in certain southern ocean regions may have influenced local ecosystems. Submarine volcanic systems release heat and minerals into surrounding waters. While unlikely to alter large-scale climate, localized effects could create biologically productive zones attractive to marine species. Another piece involves carbonate compensation depth, the ocean depth below which calcium carbonate dissolves faster than it accumulates. Changes in this depth over geological time affect fossil preservation. Shifts towards shallower compensation depths during cooler periods reduce preservation of calcareous fossils. Warmer intervals with deeper compensation depths enhance preservation, potentially biasing the fossil record toward warmer phases. All these geological indicators combine gradually. No single line of evidence proves that Megalodon routinely reached Antarctic waters, but together they outline feasible pathways. Warmer intervals, productive continental shelves, evolving ocean gateways, and sediment evidence of stable marine conditions all reduce barriers that might otherwise seem insurmountable. Scientific caution remains essential. Geological reconstructions involve uncertainties, especially when extrapolating across millions of years. Models improve continually as new data emerge. Interpretations that seem strong today may be refined tomorrow with additional evidence. Nevertheless, the geological context increasingly supports the idea that southern ocean environments during certain periods were not as restrictive as modern conditions might suggest. Marine corridors existed, warm water incursions occurred, productive ecosystems developed. These factors collectively make occasional megalodon movement into higher southern latitudes scientifically plausible. Understanding those geological trails also sets the stage for examining ocean current behavior more closely. Currents act as both barriers and highways in marine ecosystems. Their strength, direction, and temperature distribution influence where species can travel and where prey concentrates. With geological groundwork established, attention naturally shifts toward reconstructing those ancient current systems and how they may have guided large marine predators farther south than previously assumed. Once the geological setting starts to come into focus, the next piece involves the movement of water itself. Oceans are not static bodies. They circulate constantly, driven by wind, temperature differences, salinity gradients, and the slow but persistent shaping influence of continental positions. Those circulating systems determine where heat travels, where nutrients concentrate, and where marine life tends to gather. During the Miocene and Pliocene epochs, where Megalodon lived, ocean currents differed in subtle but important ways from what exists today. Understanding those differences helps explain how southern waters might have been more accessible, biologically active, and occasionally attractive to large marine predators. Ocean circulation works largely through what scientists call thermohaline circulation, sometimes described informally as the global conveyor belt. Temperature and salinity differences cause water masses to sink, rise, and move horizontally across ocean basins. Warm water tends to remain near the surface, flowing from equatorial regions toward higher latitudes. Cooler, denser water sinks and eventually returns toward lower latitudes at depth. This system distributes heat globally, moderating climates and sustaining marine ecosystems. During the Miocene climatic optimum, roughly 17 to 14 million years ago, global temperatures were higher than present averages. Warmer atmospheric conditions meant warmer surface waters across many ocean basins. Climate modelling based on sediment cores, microfossil assemblages, and isotope data indicates that equatorial heat transport toward the poles was more efficient. That does not mean Antarctica had tropical seas, but it does suggest less extreme thermal contrast than today. At that time, the Antarctic circumpolar current, which now encircles Antarctica with cold water, was still developing. The opening of the Drake Passage and Tasman Gateway allowed this current to form gradually, but its strength increased over millions of years rather than appearing suddenly. Early in its development, partial mixing between southern polar waters and mid-latitude oceans likely occurred. Such mixing could create corridors of relatively milder water, extending farther south than present conditions allow. These corridors matter biologically. Marine species often follow temperature gradients rather than fixed geographic boundaries. If warm currents extend southward seasonally or persistently, prey species can inhabit those regions. Predators then follow. Modern examples include tuna, sharks, and whales, tracking warm eddies into cooler latitudes when food availability increases. Nutrient transport accompanies heat transport. Upwelling zones occur where winds and currents bring deep, nutrient-rich water toward the surface. Those nutrients fuel plankton blooms. Plankton forms the base of marine food chains, supporting fish populations and ultimately marine mammals. Geological evidence suggests strong upwelling along certain Miocene continental margins in the southern hemisphere, especially near what are now southern Australia, New Zealand, and southern South America. Plankton productivity leaves detectable signatures. Diatomaceous sediments, rich in microscopic algae remains, accumulate in productive waters. Several Southern Ocean sediment cores from Miocene intervals show elevated diatom content, indicating sustained biological productivity. That productivity would have supported fish schools, which in turn attract larger predators. Wind patterns also influence ocean currents. Atmospheric circulation during the Miocene appears to have differed slightly due to altered temperature gradients and continental configurations. Some climate models suggest weaker circumpolar winds at certain intervals, reducing the isolation effect around Antarctica. Reduced wind-driven current strength allows more mixing between water masses, potentially extending habitable conditions farther south. Salinity gradients further shape circulation. Freshwater input from precipitation, river discharge, and ice melt alters seawater density. During warmer climatic phases with less extensive Antarctic ice, freshwater input patterns would differ. Changes in salinity influence how water masses sink or remain at the surface, affecting vertical mixing and nutrient distribution. Sea level fluctuations add another layer. Higher sea levels during warmer periods submerged continental shelves extensively. Shallow shelf seas often warm more readily than deep ocean basins due to solar heating. These warmer shelf environments can extend temperature gradients southward along continental margins, forming pathways for marine species. Ocean gateways again play a role. Even after Antarctica separated from other continents, the depth and width of connecting passages continued evolving. Shallow sills restrict deep water flow while allowing surface exchange. Geological evidence indicates variable sill depths in southern gateways during the Miocene. Such variability would influence how much warm surface water reached southern latitudes. Modern analogues provide perspective. Today, warm core eddies occasionally detach from major currents like the Gulf Stream and travel into cooler regions. These eddies carry heat, nutrients, and marine life. Similar processes likely occurred in ancient oceans. potentially allowing temporary warm water incursions towards southern polar zones. Marine mammals respond strongly to these productivity patterns. Baleen whales, for instance, migrate to regions with dense plankton blooms. Fossil whale distributions in southern hemisphere Miocene deposits suggest seasonal feeding grounds that extended farther south during warmer intervals. A predator specializing in marine mammals would logically track such movements. Another interesting factor involves oxygen minimum zones. These are regions of low dissolved oxygen at certain ocean depths, often linked to high productivity and limited circulation. Geological proxies suggest changes in oxygen minimum zone extent during the Miocene. Such changes influence fish distribution, which in turn affects predator behavior. Temperature stratification in oceans determines habitat layers. Warmer surface layers over cooler deep waters create thermoclines. The position and strength of these thermoclines shift with climate. Miocene evidence suggests somewhat weaker stratification in certain regions, promoting vertical mixing and nutrient availability. Phytoplankton species composition also shifts with temperature and nutrient conditions. Fossilized plankton assemblages from southern sediments show species typical of temperate waters during certain Miocene intervals. These assemblages align with isotope-based temperature reconstructions, suggesting milder conditions than today. Ocean acidification patterns differ across geological periods. Carbon dioxide levels during the Miocene influence seawater chemistry. Carbonate preservation in sediments indicates conditions that supported extensive calcareous plankton populations. Such populations contribute significantly to marine food webs. Continental runoff supplies trace nutrients like iron, which can stimulate phytoplankton growth. Geological evidence indicates periods of increased erosion from southern land masses during tectonic uplift phases. Enhanced nutrient input could boost productivity in adjacent seas. Hydrographic modelling studies simulate ancient ocean conditions using reconstructed continental positions and atmospheric parameters. These models often show warmer surface currents penetrating farther south than modern equivalents, though exact extents vary depending on assumptions. Marine isotope stage records provide finer temporal resolution. Fluctuations in oxygen isotope ratios from deep-sea cores reflect global ice volume and temperature cycles. Correlating these records with fossil distributions helps align biological evidence with climatic phases. Shallow marine basins along southern continental margins sometimes acted as semi-enclosed seas. These basins could retain warmth seasonally, supporting localized ecosystems distinct from open ocean conditions. Fossil assemblages in such basins sometimes include Megalodon teeth. Predator energy requirements must be considered. Large sharks require substantial caloric intake. Regions with high marine productivity provide necessary prey density. Ocean current systems that concentrate nutrients and prey species create attractive hunting grounds regardless of latitude. Migratory pathways in marine environments rarely follow straight lines. Animals often track temperature fronts, prey density gradients, or oceanographic features like seamount chains. Geological evidence of such features in southern oceans suggests potential ecological corridors. Climate variability across the Miocene and Pliocene included both warming and cooling phases. Megalodon persisted through multiple cycles, implying ecological flexibility. Its eventual extinction coincides with intensified cooling and further strengthening of Antarctic isolation. Understanding ancient currents helps explain not only where Megalodon might have travelled, but why those journeys would make ecological sense. Warm currents, nutrient-rich upwelling, accessible continental shelves, and migrating prey species combine into a coherent environmental picture. Scientific caution continues to guide interpretation. Ocean current reconstructions rely on indirect evidence, model simulations, and proxy data. While increasingly sophisticated, these methods carry uncertainties. Nevertheless, the convergence of geological, chemical, and biological evidence supports the plausibility of southern excursions. With ocean circulation patterns providing potential pathways, the next question centres on food availability itself. Predators rarely travel far without incentive. Examining the distribution of prey species, particularly marine mammals and large fish populations in southern oceans during the Miocene and Pliocene, adds another crucial piece to the overall picture. When the discussion turns from water movement to living ecosystems, one very practical question naturally comes forward. Even if warmer currents occasionally reach southern latitudes, and even if geological pathways existed, a large predator would only travel there if food was reliably available. Marine predators, especially ones the size of Megalodon, cannot afford exploratory trips without a clear energetic return. Sustaining a body estimated at tens of tons requires dense, predictable prey resources. That means examining what kinds of animals lived in southern oceans during the Miocene and Pliocene, how abundant they were, and whether those ecosystems could realistically support an apex predator of that scale. Marine mammals stand out immediately in that discussion. The Miocene epoch in particular is often described as a golden age for whale diversification. Baleen whales expanded in size and diversity. Toothed whales developed new ecological niches, and early pinnipeds, seals, sea lions and walruses began spreading into various marine environments. Fossil deposits from southern hemisphere coastal regions show strong representation of these animals. Some species appear in latitudes considerably closer to Antarctica than modern whale breeding grounds. Whales migrate today primarily to follow food availability. Baleen whales, for example, spend much of their time in nutrient-rich feeding grounds where plankton blooms support large krill populations. Geological evidence suggests that similar productivity patterns existed during warmer Miocene intervals in southern oceans. Sedimentary layers rich in diatoms, a type of plankton, indicate sustained primary productivity. Where plankton thrives, small fish gather, followed by larger fish and marine mammals. Large whales provide substantial caloric rewards for predators. Even a single successful hunt could sustain a large shark for extended periods. Bite marks on fossilised whale bones, attributed to Megalodon based on tooth spacing and serration patterns, appear in several southern hemisphere sites. These marks include deep gouges consistent with active predation rather than simple scavenging. Some whale fossils show healed injuries, indicating encounters where prey survived initial attacks. Seal fossils also contribute important context. Early pinniped species inhabited southern coastlines during the Miocene. Their presence indicates coastal ecosystems capable of supporting air-breathing marine mammals with significant energy requirements. Seals represent smaller prey than whales, but still offer considerable nutritional value. Modern great white sharks frequently target pinnipeds, suggesting an ecological model that could extend to larger prehistoric relatives. Fish populations form another critical layer. Fossil fish assemblages recovered from southern marine sediments include species adapted to temperate conditions rather than extreme cold. Otoliths, small ear bones used for balance in fish, fossilise well and provide detailed information about species composition. Many southern Miocene deposits show diverse fish communities, including schooling species that often attract large predators. Cephalopods, including squid and early cuttlefish relatives, also appear in southern fossil records. These animals play key roles in marine food webs. While not necessarily primary megalodon prey, their abundance supports fish populations that eventually sustain higher predators. Indirect ecological support can be just as important as direct prey availability. Productivity in polar adjacent regions often depends on seasonal sunlight cycles. Extended daylight during polar summers stimulates plankton blooms. Even today, Antarctic waters experience intense seasonal productivity despite cold temperatures. During warmer Miocene conditions, similar seasonal cycles likely operated, but with less thermal stress on marine species. Such cycles could create seasonal feeding opportunities attracting migratory predators. Nutrient input from continental runoff influences these ecosystems as well. Rivers and coastal erosion deliver minerals that stimulate phytoplankton growth. Geological evidence indicates active erosion along southern continental margins during parts of the Miocene, increasing nutrient availability in adjacent seas. Enhanced productivity would cascade upward through the food chain. Marine bird fossils from southern deposits provide additional ecological signals. Seabirds rely heavily on fish populations. Their presence suggests sustained fish abundance rather than sporadic productivity. While birds themselves are unlikely megalodon prey, they indicate a functioning marine ecosystem capable of supporting multiple trophic levels. Temperature tolerance of prey species matters too. Some marine mammals and fish species can operate across broad temperature ranges. Modern whales feed in cold polar waters despite breeding in warmer regions. Fossil whale distribution suggests similar ecological flexibility during the Miocene, reinforcing the idea of productive southern feeding grounds. Competition among predators also influences distribution. The Miocene oceans hosted multiple large predatory species, including other sharks and early-toothed whales, capable of hunting sizable prey. Ecological modelling suggests niche partitioning, where different predators specialise in slightly different prey types or habitats. Megalodon's size and bite force likely allowed targeting of larger marine mammals, reducing direct competition. Energy efficiency plays a role in migration decisions. Large marine animals often exploit ocean currents to minimise energy expenditure during travel. If warm currents carried prey species southward seasonally, predators could follow with relatively lower energetic cost. That dynamic appears in modern marine ecosystems and likely operated similarly in prehistoric oceans. Fossil distribution of plankton itself offers indirect evidence. Diatom-rich sediment layers correlate with periods of high productivity. Southern ocean cores frequently show such layers during warmer Miocene intervals. These primary producers underpin entire marine ecosystems, making higher trophic level presence plausible. Some researchers also examine nitrogen isotope ratios in fossil remains to estimate trophic levels. Higher ratios generally indicate higher positions in the food chain. Preliminary studies on associated marine mammal fossils from southern deposits suggest robust predator-prey structures consistent with apex predator presence. Shallow continental shelf environments remain particularly important. These areas combine sunlight penetration, nutrient mixing, and structural habitat complexity. Geological mapping indicates extensive Miocene shelf environments around parts of southern continents. These habitats often serve as feeding grounds for marine mammals and fish alike. Marine ecosystem stability affects predator presence as well. Short-lived productivity spikes might attract temporary visitors, but sustained ecosystems support regular seasonal migration. Fossil evidence suggesting repeated marine mammal presence in southern regions across multiple stratigraphic layers points toward relatively stable feeding grounds. Climate fluctuations within the Miocene and Pliocene complicate the picture slightly. Warmer intervals alternated with cooling phases. Predator distribution likely shifted accordingly. Some southern Megalodon evidence corresponds specifically to warmer intervals, reinforcing the climate-prey connection. Another ecological factor involves reproductive cycles. Some marine mammals give birth in warmer waters but feed in cooler ones. If prehistoric species followed similar patterns, predators could encounter concentrated prey during migration transitions. These predictable seasonal gatherings often become focal hunting opportunities. Acoustic ecology deserves mention too. Marine mammals rely heavily on sound. Predators capable of detecting acoustic cues might locate prey over considerable distances. While direct evidence of megalodon sensory capabilities remains limited, comparisons with modern sharks suggest strong vibration detection abilities. Biological productivity ultimately determines whether a region can sustain an apex predator. Evidence from southern Miocene deposits consistently indicates productive marine ecosystems. Plankton blooms, fish diversity, marine mammal abundance, and stable shelf habitats combine into a plausible ecological foundation. scientific caution remains necessary. Prey presence does not guarantee predator presence. Ecosystems can support potential predators that never arrive due to behavioral or physiological constraints. However, when environmental suitability, geological pathways, ocean current patterns, and prey availability all align, the probability of at least occasional predator movement increases. As additional fossil evidence accumulates and analytical techniques improve, researchers continue refining these ecological reconstructions. Each new whale, fossil, fish assemblage, or plankton record adds detail. Gradually, a clearer image of southern Miocene oceans emerges, one far more biologically active than modern Antarctic waters. With prey availability established as a plausible driver, comparisons with modern shark behaviour become increasingly relevant. Examining how living large sharks migrate, tolerate temperature variation, and follow prey provides useful analogues for interpreting Megalodon's possible southern excursions without relying solely on fossil evidence. Once the fossil evidence, climate reconstructions, and prey availability begin forming a coherent picture, comparisons with modern sharks become especially useful. While Megalodon has no living descendants in the strict evolutionary sense, several modern shark species provide functional analogues. Studying their physiology, behaviour, migration patterns, and ecological strategies allows scientists to estimate how a very large prehistoric shark might have operated in similar environmental conditions. This approach does not assume direct equivalence, but it offers grounded biological context instead of speculation. The great white shark usually enters the conversation first. At around 5 to 6 meters in length, it is significantly smaller than Megalodon, yet it shares certain anatomical traits. Serrated triangular teeth, powerful jaws, and a diet including marine mammals make it a practical behavioural comparison. Modern tracking studies using satellite tags show great whites travelling across entire ocean basins. Some individuals migrate thousands of kilometres annually, crossing temperature gradients that range from warm subtropical waters to considerably cooler temperate zones. These migrations are rarely random. They follow prey movements, breeding cycles, and seasonal productivity shifts. For example, great whites off South Africa regularly patrol seal colonies in relatively cool waters, despite having access to warmer habitats elsewhere. This demonstrates physiological tolerance combined with strong ecological motivation. If a 6-meter shark can maintain activity in cooler waters when prey is abundant, it becomes reasonable to consider that a larger shark with potentially similar adaptations might do the same on a broader scale. Physiological temperature regulation plays a key role here. Certain modern sharks exhibit regional endothermy. Through specialized vascular structures called rete mirabile, they retain metabolic heat generated by muscle activity. This adaptation keeps critical organs and swimming muscles warmer than surrounding water, improving performance in cooler conditions. Great whites, short-fin mako sharks, and salmon sharks display this capability. Although direct evidence for Megalodon's thermoregulation is limited, tooth isotopic data and body size considerations suggest some degree of similar heat retention is plausible. Large body size itself contributes to thermal stability. A phenomenon sometimes called thermal inertia means larger animals lose heat more slowly than smaller ones. Marine mammals demonstrate this clearly, but large fish also benefit. A 20-meter shark would have substantial thermal buffering compared with smaller species. This does not eliminate temperature limits entirely, but it expands the range of tolerable conditions. Modern tiger sharks offer another useful comparison. They occupy a wide range of habitats, from tropical waters to cooler temperate regions. Their diet is extremely varied, including fish, turtles, birds, marine mammals, and carrion. Such dietary flexibility often correlates with geographic flexibility. While Megalodon likely specialised more heavily on large marine mammals, evidence of mixed feeding suggests it was not exclusively dependent on a single prey category. Whale sharks and basking sharks provide insight into size-related movement, even though their feeding strategies differ completely. These large filter feeders undertake extensive migrations following plankton blooms. Their movements demonstrate how ocean productivity patterns shape large shark distribution independent of predatory behaviour. The principle that large sharks can travel vast distances in response to food availability remains consistent. Satellite tagging of modern sharks has revealed unexpected long-distance movements. Some great whites tagged off California travel to mid-Pacific regions, sometimes referred to informally as shark gathering zones. These journeys involve crossing deep ocean areas with limited immediate prey visibility, suggesting strong navigational capabilities. Magnetic field sensitivity, temperature gradients, and chemical cues likely contribute. If Megalodon possess similar sensory systems, long-range navigation across southern ocean corridors becomes biologically plausible. Sharks detect weak electrical signals, pressure changes, and chemical gradients efficiently. These abilities would assist in locating productive feeding grounds even when those grounds shifted seasonally. Reproductive behaviour also informs geographic patterns. Many modern sharks use nursery areas where juveniles grow in relatively protected environments, often warmer shallow waters. Adults range more widely. Fossil evidence suggesting juvenile megalodon teeth in certain coastal deposits aligns with this pattern. That implies adults could undertake longer migrations without juveniles necessarily accompanying them. Energetics deserve careful consideration. Large predators balance caloric intake against travel cost. Modern large sharks often adopt energy-efficient cruising speeds rather than constant rapid swimming. Hydrodynamic modelling of Megalodon suggests a similarly efficient swimming style, with a powerful caudal fin generating steady propulsion suitable for migration. Modern porbeagle sharks offer another temperature tolerance example. They inhabit North Atlantic waters, including relatively cold regions, yet remain active apex predators. Like great whites, they exhibit regional endothermy. Their existence shows that large predatory sharks are not restricted exclusively to warm tropical zones. Dietary overlap between Megalodon and modern great whites includes marine mammals. Bite mark analyses on fossil whale bones resemble great white predation patterns but on a larger scale. Modern observations show great whites targeting weakened or juvenile whales opportunistically. Megalodon, with significantly greater size and bite force, likely expanded this strategy to adult whales more frequently. Competition among predators influences distribution as well. Today, great whites, orcas, and large sharks sometimes compete for similar prey. Orcas occasionally displace sharks from feeding areas. During the Miocene, early toothed whales capable of predation existed alongside Megalodon. Comparative ecology suggests complex predator interactions rather than simple dominance hierarchies. Swimming speed estimates derived from body modelling indicate Megalodon may have been slightly slower than some modern pelagic sharks but capable of sustained cruising. Speed is less critical than endurance for long-distance migration. Marine mammals demonstrate this principle. Steady, energy-efficient movement often outweighs bursts of speed. Shark sensory biology further supports potential range flexibility. Electroreception, olfaction, and lateral line vibration detection function across temperature gradients. These systems allow sharks to detect prey even in low visibility conditions common in productive upwelling zones. Modern shark responses to climate variability also offer perspective. As ocean temperatures shift today, some shark species expand or contract their ranges accordingly. Observations of great whites appearing farther north or south than historically recorded reflect ecological adaptability. Similar adjustments likely occurred repeatedly during Miocene climate fluctuations. Social behaviour among sharks remains less understood, but temporary aggregations around abundant prey are documented. Whale carcasses, seal colonies, and fish spawning events attract multiple predators simultaneously. Fossil assemblages containing multiple megalodon teeth in similar stratigraphic contexts may reflect such aggregations. Comparisons also highlight differences. Modern sharks face human pressures including fishing, habitat disruption, and pollution. Megalodon operated in ecosystems without those influences. Prehistoric marine mammal populations may have been larger, providing more consistent prey resources. Extinction patterns provide indirect comparison. Megalodon disappeared during a period of global cooling and ecological restructuring. Some modern shark species show sensitivity to temperature changes affecting prey distribution. That historical precedent underscores the importance of climate in shaping predator ranges. Despite similarities, caution remains necessary. Evolutionary distance between Megalodon and modern sharks means behaviours cannot be assumed identical. Functional analogues guide interpretation, not definitive conclusions. The cumulative comparison suggests that a large predatory shark with partial thermoregulation, migratory prey reliance, and efficient swimming capabilities could plausibly extend its range into cooler southern waters under favourable climatic conditions. Modern sharks demonstrate each of these traits separately. Combining them in a larger prehistoric species remains consistent with available evidence. With biological comparisons providing context, attention begins shifting toward chemical signatures preserved directly within fossils. Isotopic analyses and trace element studies offer increasingly precise environmental information, refining estimates of water temperature and habitat conditions experienced by Megalodon individuals across different regions. Once the biological comparisons begin to make sense, attention often turns to the subtler forms of evidence, the kind that cannot be seen without laboratory instruments. Fossils are not only shapes and sizes preserved in stone, they also carry chemical traces from the environments where the animals once lived. These traces, preserved at microscopic scales inside enamel, bone, and surrounding sediments, act almost like environmental recordings. They do not speak loudly, but when interpreted carefully, they can reveal water temperature, diet, migration patterns, and sometimes even seasonal changes. For Megalodon, especially when considering possible southern movement toward cooler waters, these chemical signatures provide some of the most informative clues. The most frequently discussed method involves stable isotope analysis. Oxygen isotopes, in particular, are widely used in marine paleontology. Oxygen atoms exist in slightly different forms, mainly oxygen-16 and oxygen-18. The ratio between these isotopes in biological tissues reflects the temperature of the water in which the organism lived. Warmer water tends to produce lower oxygen-18 ratios in tooth enamel, while cooler water increases that proportion. Because shark teeth mineralize with relatively stable chemical structures, they can preserve this isotopic ratio for millions of years. Researchers collect extremely small enamel samples using microdrills or laser ablation tools. These samples undergo mass spectrometry analysis, which measures isotope ratios with high precision. The resulting values are then compared with modern calibration datasets. Scientists use living marine animals from known temperature environments to establish how isotope ratios correspond to water temperature. Applying these calibrations to fossil specimens produces estimated temperature ranges rather than exact numbers, but even approximate distinctions between tropical, temperate and cooler waters are highly valuable. Some Megalodon teeth from southern hemisphere deposits show isotope values suggesting formation in waters cooler than what earlier assumptions predicted. This does not immediately mean Antarctic residency, but it indicates a capacity for operating in temperate or even borderline cool environments. Repeated findings across different regions strengthen confidence that these are genuine environmental signals rather than anomalies. Carbon isotopes provide complementary information. Carbon-12 and carbon-13 ratios in tooth enamel reflect aspects of diet and trophic position. Marine mammals, fish, and plankton-based food chains leave distinct carbon signatures. Megalodon teeth frequently show carbon isotope values consistent with high trophic levels, aligning with predation on large marine mammals. When southern fossil teeth display similar signatures, they suggest consistent feeding behaviour across geographic ranges. Trace element chemistry expands the analytical toolkit further. Elements such as strontium, barium, magnesium, and zinc incorporate into mineralized tissues in small concentrations. Their relative abundance can reflect salinity, water chemistry, and ecological conditions. For instance, strontium ratios often vary between open ocean water and coastal environments. If a tooth shows shifting strontium levels along its growth axis, it may indicate movement between habitats with different salinity profiles. Barium levels sometimes correlate with productivity zones. Upwelling regions, where nutrient-rich deep water reaches the surface, often show elevated barium concentrations in marine organisms. Some southern Megalodon specimens exhibit trace element patterns consistent with productive shelf environments, rather than deep tropical open ocean settings. Tooth growth patterns also allow sequential sampling. Teeth mineralize gradually, and chemical composition can vary slightly during formation. By analyzing different sections of a single tooth, researchers sometimes reconstruct environmental changes experienced during the shark's life. While resolution is limited compared with tree rings, it can still suggest movement between temperature zones. Another useful chemical proxy involves rare earth elements absorbed during fossilization. These elements reflect surrounding sediment chemistry. If tooth chemistry matches local sediment signatures, it strengthens the argument that fossilization occurred near the original habitat rather than after long-distance transport. Nitrogen isotope analysis occasionally appears in studies of associated marine mammal fossils from the same deposits. High nitrogen 15 levels typically indicate higher trophic positions. When these associated fossils suggest rich predator-prey hierarchies, the ecological context supporting Megalodon presence becomes clearer. Diagenesis remains a persistent concern. After burial, chemical changes can alter original isotopic signatures. Groundwater movement, mineral replacement, and temperature shifts during geological processes all influence fossil chemistry. Scientists address this by examining enamel microstructure integrity, comparing multiple specimens, and screening samples for alteration indicators before drawing conclusions. Advances in synchrotron imaging allow extremely fine-scale chemical mapping without destroying samples. This technique uses high-energy radiation to detect elemental distribution across tooth structures. It helps distinguish original biological signals from later contamination. Laser ablation inductively coupled plasma mass spectrometry, often abbreviated but rarely spoken casually, has become another standard method. It allows targeted sampling at micrometer scales, revealing chemical gradients along tooth growth lines. Such gradients sometimes correlate with seasonal environmental changes. Comparative baselines from modern sharks remain essential. Researchers analyze teeth from living species inhabiting known temperature gradients to validate interpretations. For example, great white sharks sampled across temperate zones show isotopic ranges overlapping with some fossil Megalodon specimens, reinforcing the plausibility of similar temperature tolerance. Marine sediment chemistry also contributes indirectly. Oxygen isotope records from foraminifera shells, microscopic plankton preserved in sediments, provide independent temperature estimates. Aligning these with Megalodon tooth isotope data strengthens environmental reconstructions. Salinity indicators in sediments offer additional context. Changes in evaporation rates, freshwater input, and ocean mixing affect salinity, which in turn influences marine ecosystem structure. Chemical proxies from southern sediments during Miocene intervals often indicate moderate rather than extreme polar salinity conditions. Phosphorus content in sediments can reflect biological productivity. Elevated phosphorus often accompanies plankton-rich environments. Southern ocean sediment cores from relevant time periods frequently show such enrichment, supporting active food webs. Some researchers also examine calcium isotope ratios, though this approach remains less widespread. Preliminary findings suggest potential for reconstructing aspects of biomineralization and environmental conditions, but interpretation standards continue developing. organic residue analysis occasionally reveals lipid biomarkers associated with certain plankton groups. While not directly linked to Megalodon, these biomarkers help reconstruct food web foundations. Strong plankton productivity supports the higher trophic levels necessary for large predators. Another subtle indicator involves sulfur isotopes. Marine sulfur cycles respond to oxygen availability, productivity, and sediment conditions. Although more commonly applied to ancient microbial studies, sulfur isotopes occasionally inform broader marine environmental reconstructions. Cross-disciplinary integration strengthens confidence. When isotopic data from teeth align with sediment chemistry, microfossil assemblages and climate models, interpretations gain robustness. Discrepancies trigger further investigation rather than immediate conclusions. Museum collections play an important role here. Many Megalodon teeth collected decades ago lacked detailed chemical analysis at the time. Re-examining these specimens with modern techniques sometimes yields new environmental insights without additional fossil discoveries. Analytical uncertainty always remains. Calibration curves, physiological assumptions, and environmental variability introduce margins of error. Scientists emphasize ranges and probabilities rather than precise temperature figures. Public discussions sometimes oversimplify isotope findings into dramatic statements about habitat extremes. Researchers typically present more measured interpretations. Cooler than expected values indicate expanded tolerance, not necessarily polar residency. Despite caution, the convergence of chemical evidence with fossil distribution, geological context, and biological analogues gradually supports the idea of broader Megalodon habitat flexibility. Not permanent Antarctic occupation, but credible seasonal or episodic presence in southern waters during favourable climatic intervals. Chemical signatures also help track ecological change leading toward Megalodon's extinction. Progressive cooling, shifts in prey distribution, and oceanographic restructuring appear in isotopic records. These changes likely reduce suitable habitat over time. As analytical technology continues improving, resolution will increase further. New isotopic systems, refined calibration methods, and integrated climate modelling promise deeper insights. The fossil record, though incomplete, continues yielding information when examined with evolving tools. With chemical evidence providing increasingly detailed environmental context, attention often shifts toward physical landscape changes affecting marine accessibility. Sea level fluctuations, continental shelf expansion, and submerged habitat formation offer another dimension for understanding how large marine predators could move towards southern regions when conditions allowed. When the chemical clues from fossil teeth and surrounding sediments begin to outline environmental conditions, another physical factor quietly comes into focus, one that reshapes coastlines, alters habitats, and indirectly influences where marine predators can travel. Sea level does not remain fixed. Over geological time it rises and falls repeatedly, responding to climate shifts, ice volume changes, tectonic movement, and ocean temperature variations. During the Miocene and Pliocene, when Megalodon lived, sea level fluctuations played a substantial role in shaping marine ecosystems, especially along continental margins in the southern hemisphere. Warmer global climates generally correspond with higher sea levels. When polar ice sheets shrink or disappear, large volumes of water return to the oceans. At the same time, warmer seawater expands slightly in volume, a process called thermal expansion. Together, these factors raise global sea level. Geological evidence suggests that during certain Miocene intervals, sea level stood tens of meters higher than present levels. That difference might sound modest at first, but along gently sloping continental shelves it translates into vast newly submerged areas. Continental shelves are particularly important biologically. They tend to be shallow enough for sunlight penetration, which supports photosynthesis by marine plants and plankton. Nutrients from land runoff, river discharge, and coastal erosion accumulate there. These conditions foster rich food webs that attract fish, marine mammals, and ultimately apex predators. When sea level rises, shelf area expands, increasing the extent of these productive habitats. Southern Hemisphere continental shelves, especially around southern South America, Australia and New Zealand, show geological evidence of Miocene marine transgressions, periods when rising seas covered previously exposed land. Sedimentary formations from these intervals contain marine fossils indicative of productive coastal ecosystems. Megalodon teeth occasionally appear in these same sediment layers, suggesting that the shark may have used these expanded habitats as feeding grounds. The geometry of coastlines also changes with sea level. Bays deepen, estuaries widen, and shallow inland seas can form temporarily. Such environments often become nursery grounds for marine species. Fossil evidence of juvenile megalodon teeth in certain coastal deposits supports the idea that some shallow marine areas serve developmental roles, although these nursery sites appear more common in warmer latitudes. Migration corridors sometimes open or close depending on sea level. When seas rise, previously exposed land bridges disappear, allowing marine species to pass between basins. Conversely, falling sea levels can isolate populations. During the Miocene, fluctuating sea levels likely modified oceanic connections repeatedly, influencing marine circulation patterns and biological dispersal routes. Higher sea levels also alter ocean current behaviour. Expanded shallow seas change how water masses move, affecting temperature distribution and nutrient transport. Climate models incorporating Miocene sea level reconstructions often show warmer surface waters penetrating farther south along continental margins when shelves were extensive. Another effect involves sediment deposition. Rising seas slow coastal erosion in some areas while increasing sediment accumulation in others. Thick marine sediment layers form during prolonged high stand periods. These layers preserve fossils more effectively, increasing the likelihood that evidence of southern megalodon presence survives to the present day. Sea level changes interact closely with glacial cycles. Although Antarctic glaciation began before the Miocene, ice extent fluctuated considerably. Periods of reduced ice corresponded with higher sea levels and warmer coastal conditions. Geological records show alternating glacial and interglacial phases, each leaving distinct sedimentary signatures. Isostatic adjustment complicates this picture further. As ice accumulates on land, its weight depresses the crust. When ice melts, the land gradually rebounds. This vertical movement can either amplify or counteract global sea level changes locally. Antarctic coastal regions show evidence of such adjustments across geological timescales. Marine productivity often increases during transgressive phases. Newly submerged land releases nutrients into the ocean, stimulating plankton growth. Fossil diatom assemblages from Miocene southern sediments frequently correspond with known high sea level intervals, indicating enhanced primary productivity. Whale fossil distributions align with some of these transgressive phases as well. Expanded shelf environments likely supported abundant feeding grounds for marine mammals. If megalodons specialize partly on marine mammal prey, following these expanding habitats would make ecological sense. Sea level fluctuations also influence salinity patterns. Expanded coastal seas mix freshwater runoff with ocean water differently than narrow coastlines do. Changes in salinity affect marine species distribution, sometimes favouring particular fish populations that serve as intermediate prey. Coral reef distribution offers indirect clues about sea level. Reef-building corals require specific depth and temperature conditions. Fossil coral assemblages in southern hemisphere Miocene deposits indicate periods of relatively warm, shallow seas, extending farther south than today, reinforcing the broader climate context. Submerged river valleys preserved in seismic surveys provide additional evidence. These paleovalleys formed when sea levels were lower and later flooded as levels rose. Mapping their distribution helps reconstruct past shoreline positions and marine habitat extent. Marine terrace formations along some southern coastlines record successive sea level high stands. These terraces, essentially ancient shorelines now elevated by tectonic uplift, often contain marine fossils including shark teeth. Dating these terraces provides chronological anchors for interpreting fossil distribution. Another consequence of higher sea levels involves predator-prey encounter rates. Expanded shallow habitats concentrate marine mammals seasonally. Narrower continental shelves today sometimes limit such concentration zones, but Miocene high stands likely provided broader feeding areas. Temperature moderation also occurs in shallow seas. Sunlight warms shallow water more effectively than deep ocean water. During warmer climatic phases, this effect could extend temperate conditions southward, along continental margins, supporting diverse marine ecosystems. Modern analogues illustrate similar processes. Regions like the North Sea, relatively shallow and productive, support abundant marine life due partly to their bathymetry. Ancient southern shelf seas may have functioned similarly during Miocene high stands. Fossil mollusk assemblages contribute further insight. Many mollusk species have narrow environmental tolerances. Southern Hemisphere Miocene mollusk fossils often indicate moderate temperatures and productive shallow waters, aligning with high sea level reconstructions. Geochemical proxies in sediments, such as strontium isotope ratios, help track sea level changes globally. These proxies, combined with fossil evidence, refine timelines for marine transgressions and regressions relevant to Megalodon's existence. Despite these correlations, caution remains necessary. High sea levels create opportunity but do not guarantee predator presence. Biological, behavioral, and physiological factors still determine whether species exploit available habitats. Nevertheless, the combination of expanded continental shelves, warmer shallow waters, increased marine productivity, and accessible migration pathways strengthens the case that southern marine environments during certain Miocene intervals could support large apex predators at least seasonally. Ongoing research continues refining sea level reconstructions. Improved dating techniques, better seismic imaging, and expanded drilling programs gradually enhance resolution. Each new data set adds context to fossil findings, sometimes confirming earlier interpretations, sometimes prompting revisions. Understanding sea level dynamics also helps explain later ecological changes leading toward Megalodon's extinction. Progressive cooling, falling sea levels, and shrinking shallow habitats would reduce feeding grounds and migration corridors over time. With sea level influences considered, attention often shifts toward the broader ecological communities preserved alongside Megalodon fossils. Examining associated marine species provides further context for reconstructing the ecosystems these sharks may have entered when southern conditions permitted. Once sea level changes, ocean currents and fossil chemistry begin aligning into a coherent environmental picture. Another important line of evidence emerges from the organisms found alongside Megalodon remains. Fossils rarely appear in complete isolation. They tend to occur within assemblages, groups of species preserved together in the same sediment layers. These associated marine fossils provide ecological context. They help answer a simple but crucial question. If Megalodon teeth are present in certain southern deposits, what other animals lived there at the same time, and what does that tell us about environmental suitability? Whale fossils are among the most informative associated remains. The Miocene epoch saw a major expansion in whale diversity. Baleen whales evolved larger body sizes, developed new feeding strategies, and spread into a wide range of marine environments. Southern Hemisphere fossil sites, particularly in regions like southern South America, New Zealand, and southern Australia, frequently contain whale bones in the same stratigraphic layers as Megalodon teeth. These whale fossils often show bite marks consistent with large shark predation. Those bite marks matter because they reflect interaction rather than coincidence. The spacing and serration patterns correspond closely with known Megalodon tooth morphology. Some whale bones display healing around bite scars, indicating that the animal survived attacks. Others show more extensive damage, suggesting successful predation or scavenging. Either way, the ecological link becomes clear. Large marine mammals were present in southern waters, and at least occasionally, large sharks interacted with them there. Seal fossils also appear in several southern Miocene marine deposits. Early pinniped species occupied coastal regions where productive marine ecosystems provided fish and squid. Modern sharks frequently target seals as prey, especially in areas where seal colonies gather predictably. The presence of seals in ancient southern ecosystems suggests another potential food source that could attract a large predator seasonally. Fish assemblages provide further supporting context. Fossilized fish, vertebrae, scales, and especially otoliths, those small ear bones fish use for balance, preserve well in marine sediments. Otolith analysis allows species identification and environmental reconstruction because different fish species prefer different temperature ranges and habitats. Southern Hemisphere Miocene fish assemblages frequently include temperate water species rather than exclusively cold-adapted forms. That aligns with climate reconstructions indicating milder conditions during certain intervals. Cephalopod remains, including fossilized squid beaks and shell fragments from nautiloid relatives, appear in some southern marine deposits as well. These animals occupy mid-level trophic positions in marine food webs. Their presence indicates active ecosystems with sufficient productivity to sustain higher predators. While Megalodon likely focused on larger prey, abundant cephalopods support fish populations that form indirect prey networks. Marine bird fossils add another layer of ecological information. Seabirds rely heavily on fish populations. Fossil seabird bones found in southern Miocene deposits suggest sustained fish abundance over extended periods. Although birds themselves are unlikely Megalodon prey, they serve as indicators of ecosystem stability and productivity. Plankton microfossils play a particularly important role in environmental reconstruction. Diatoms, foraminifera, and coccolithophores leave microscopic shells preserved in sediments. Their species composition shifts predictably with water temperature, nutrient availability, and salinity. Southern ocean sediment cores from Megalodon time periods frequently show plankton assemblages indicative of temperate rather than extreme polar conditions. Mollusk fossils offer additional temperature clues. Many marine mollusks have narrow environmental tolerances. Fossil assemblages containing species analogous to modern temperate water mollusks reinforce the interpretation of relatively mild southern seas during certain Miocene intervals. These organisms also form part of broader marine food webs, contributing to ecosystem productivity. Marine reptile fossils, though less common in Miocene deposits than earlier periods, occasionally appear in southern hemisphere sediments. Their presence indicates ecological continuity from earlier marine ecosystems into the time when Megalodon lived, further suggesting that southern waters remained biologically active rather than barren. Coral fossils occasionally appear in southern hemisphere Miocene strata as well. While not as extensive as tropical reef systems, these corals indicate localized warm water conditions sufficient to support reef-building organisms. Coral presence supports the broader climate reconstruction of warmer southern seas. Sedimentology complements fossil evidence. Grain size, layering patterns, and mineral composition help reconstruct depositional environments. Many southern fossil assemblages containing Megalodon teeth occur in sediments consistent with continental shelf environments rather than deep ocean basins. Shelf environments typically support higher productivity. Isotopic analysis of associated fossils strengthens environmental interpretation. Oxygen isotope ratios in mollusk shells, whale bones, and plankton microfossils often align with Megalodon tooth isotope readings, suggesting consistent environmental conditions across multiple species. Taphonomy, the study of how organisms become fossilized, also matters. The condition of associated fossils helps determine whether remains accumulated locally or were transported. Well-preserved articulated skeletons suggest minimal transport. reinforcing local habitat interpretations. Fossil diversity within assemblages provides insight into ecosystem complexity. High species diversity typically indicates stable, productive environments capable of supporting multiple trophic levels. Several southern Miocene sites show such diversity, supporting the idea of viable apex predator habitats. Some fossil sites show repeated layers containing similar assemblages across time, indicating persistent environmental conditions rather than brief anomalies. This repetition strengthens arguments for sustained ecosystem suitability. Shark fossils other than Megalodon occasionally appear in the same deposits. Smaller shark species with known temperature preferences help calibrate environmental interpretation. Their coexistence suggests overlapping ecological niches within temperate marine environments. Marine mammal bone density within certain deposits indicates frequent presence rather than occasional stranding events. Such density supports the idea of regular marine mammal migration through these regions. Plant-derived organic matter in marine sediments indicates terrestrial runoff, which often stimulates marine productivity. Fossil pollen grains found in some southern marine deposits suggest nearby vegetated landmasses, contributing nutrients to coastal waters. Trace fossil evidence, such as burrows and feeding marks in sediments, reflects benthic ecosystem activity. Active seafloor communities support broader food webs extending upward to larger predators. Comparative analysis across multiple southern hemisphere sites reveals similar ecological patterns despite geographic separation. This consistency suggests widespread environmental conditions rather than isolated local anomalies. Scientific caution still applies. Associated fossils indicate ecological possibility, but not definitive predator presence. However, when megalodon teeth appear within these diverse productive assemblages, the ecological case strengthens. Research continues expanding these datasets. New fossil discoveries, refined dating methods, and improved analytical techniques gradually increase resolution. Museum collections continue yielding new insights when revisited with modern tools. Understanding associated marine fossils also helps explain later ecological transitions. As climates cooled and Antarctic isolation intensified, many warm temperate species declined or shifted range. Such changes likely affected megalodon habitat availability. With ecosystem context established through associated fossils, attention often moves toward reconstructing entire food webs. Understanding how energy flowed through these ancient southern marine systems helps clarify how a large apex predator might fit into the broader ecological structure without relying on isolated evidence alone. When individual fossils begin forming recognizable patterns, the next step usually involves stepping back and looking at the larger ecological structure they imply. Instead of focusing on single species, researchers try to reconstruct entire food webs, the networks of energy flow that connect plankton, fish, marine mammals, and apex predators. This broader perspective helps determine whether southern ocean ecosystems during the Miocene and Pliocene could realistically support a predator as large as Megalodon. A complete food web offers stability, redundancy, and consistent energy supply. Without that foundation, even the most adaptable predator struggles to persist. At the base of these ancient Antarctic-adjacent ecosystems were microscopic primary producers. Phytoplankton, including diatoms and coccolithophores, formed the primary energy entry point. Fossil diatom deposits in southern marine sediments indicate repeated periods of high productivity. These microscopic algae depend on sunlight, dissolved carbon dioxide, and nutrients such as nitrogen, phosphorus, and iron. Geological evidence suggests that during warmer Miocene intervals, nutrient delivery to southern oceans was relatively strong due to continental runoff, upwelling currents, and less extensive permanent ice coverage. Diatomaceous sediment layers, sometimes several meters thick, demonstrate sustained plankton blooms rather than brief events. Such productivity supports the entire marine food chain. Modern Antarctic waters, even though cold, remain highly productive seasonally for similar reasons. During the Miocene, warmer temperatures likely enhanced this productivity further by extending growing seasons and improving nutrient mixing. Zooplankton occupied the next trophic level. Small crustaceans, larval organisms, and early krill relatives grazed on phytoplankton. Although soft-bodied zooplankton rarely fossilized directly, indirect evidence comes from preserved exoskeleton fragments, fecal pellet structures, and chemical signatures in sediments. These organisms convert microscopic plant energy into animal biomass accessible to larger species. Fish populations formed a critical intermediate link. Fossil fish remains in southern Miocene deposits include both small schooling fish and larger predatory species. Otolith analysis suggests diverse fish communities occupying different ecological niches, from surface feeders to deeper water hunters. Schooling fish in particular provide efficient energy transfer upward in the food web because they concentrate biomass in predictable locations. Cephalopods such as squid and early cuttlefish relatives contributed another important mid-level trophic group. Fossil beaks and shell fragments indicate their presence in southern marine environments. These animals serve as prey for both fish and marine mammals, while also acting as active predators themselves. Their rapid growth and reproductive cycles make them effective energy conduits within marine ecosystems. Marine mammals occupied higher trophic levels. Baleen whales fed primarily on plankton and small fish, converting lower-level biomass into large-bodied animals. Fossil whale assemblages from southern hemisphere Miocene deposits suggest seasonal feeding grounds in temperate southern waters. Toothed whales, including early sperm whale relatives, functioned as predators targeting fish and squid. Seals and early pinnipeds added further complexity. Fossil evidence indicates coastal colonies where fish abundant supported breeding populations. Pinnipeds often act as both predators and prey within marine food webs. Modern ecosystems show similar dynamics, with sharks and orcas occasionally targeting seals. Large fish predators also existed alongside Megalodon. Fossil evidence of other large shark species, as well as predatory bony fish, suggests multi-layered predatory hierarchies. Such complexity reduces ecological instability because no single predator monopolizes resources entirely. Seabirds functioned as mobile indicators of fish abundance. Fossil seabird remains in southern Miocene sediments indicate sustained fish populations. While birds themselves are minor contributors to total biomass compared with marine mammals, their presence reflects ecosystem productivity. Benthic organisms, those living on or within the seafloor, formed another important component. Mollusks, crustaceans, echinoderms, and burrowing invertebrates appear frequently in southern fossil assemblages. These organisms recycle organic material sinking from upper water layers, maintaining nutrient cycling and supporting fish species that feed near the seabed. Marine plant life, including macroalgae and early kelp-like forms, likely existed along some southern coastlines during warmer intervals. Although direct fossil evidence is limited due to preservation challenges, sediment chemistry and associated fauna suggest vegetated coastal zones. Such habitats support juvenile fish populations, enhancing overall ecosystem resilience. Energy transfer efficiency determines whether apex predators can thrive. Roughly 10% of energy typically transfers between trophic levels. For a predator the size of Megalodon, lower-level productivity must be substantial. Evidence from diatom deposits, fish assemblages, and marine mammal fossils indicates sufficient productivity during certain Miocene phases. Food web stability depends not only on productivity, but also on diversity. Multiple prey species allow predators to adapt if one population fluctuates. Fossil assemblages showing diverse marine mammals, fish, and invertebrates suggest ecological redundancy. Such redundancy buffers ecosystems against short-term disturbances. Climate variability influenced these food webs over time. Warmer phases expanded productivity zones southward, while cooling phases contracted them. Megalodon's persistence across multiple climatic cycles suggests adaptability to shifting prey distributions, though eventual cooling may have reduced habitat sufficiently to contribute to extinction. Oceanographic features like upwelling zones played central roles. Where nutrient-rich deep water rose to the surface, plankton productivity surged. Geological proxies indicate such upwelling occurred along certain southern continental margins during the Miocene. These zones likely functioned as seasonal feeding hotspots. Seasonality itself structured food web dynamics. Extended daylight during polar summers stimulated productivity bursts. Migratory species timed movements accordingly. Whales, fish, and potentially large sharks may have followed these seasonal cycles, creating predictable predator-prey interactions. Predator interactions also shape food webs. Evidence of early large-toothed whales capable of active predation suggests competition with Megalodon. Such competition may have influenced geographic distribution, prey selection, and hunting strategies. Scavenging likely supplemented active predation. Whale carcasses sinking after natural death create localized feeding opportunities. Modern sharks, including great whites, exploit such events. Megalodon, given its size and bite force, likely did the same when opportunities arose. Nutrient recycling through decomposition supports continued productivity. Bacterial communities break down organic matter, releasing nutrients back into the water column. While bacterial fossils are rare, geochemical signatures in sediments indicate active microbial processes. Sediment oxygen levels influence benthic ecosystem health. Proxy indicators suggest that southern Miocene shelf environments maintain sufficient oxygenation to support diverse bottom-dwelling communities. Healthy benthic systems contribute to overall food web stability. Continental vegetation indirectly affects marine food webs through runoff. Fossil pollen in southern marine sediments indicates nearby vegetated land masses during certain periods. Plant-derived nutrients entering coastal waters stimulate productivity. Hydrothermal activity may have created localized productivity zones. Submarine volcanic systems release minerals supporting specialized ecosystems. While unlikely to sustain large predators directly, they contribute to broader nutrient cycles. Ecosystem modeling using fossil data attempts to reconstruct biomass distribution quantitatively. These models suggest that Miocene southern oceans could sustain multiple large marine predators simultaneously under favorable climatic conditions. Scientific caution persists. Food web reconstructions rely on incomplete fossil records and proxy data. Interpretations remain probabilistic rather than definitive. Still, convergence across multiple evidence types strengthens confidence. Understanding these ancient food webs clarifies that southern oceans during certain Miocene intervals were not marginal environments. They supported complex productive ecosystems capable of sustaining large marine mammals and potentially the predators that hunted them. As climate conditions shifted gradually toward cooler phases, these food webs likely restructured. Changes in plankton productivity, fish distribution, and marine mammal migration patterns would influence apex predator presence. Examining those climate shifts helps explain how environmental change may have limited Megalodon's southern range over time. When the broader structure of those ancient marine food webs begins to come into focus, another gradual process starts shaping the story in a different direction. The same environmental flexibility that once allowed warmer currents, productive ecosystems, and diverse prey populations in southern oceans did not remain constant. Over millions of years, Earth's climate moved through a series of cooling phases that steadily altered ocean conditions, reorganized ecosystems, and ultimately reduced the kinds of habitats large warm-adapted predators depended on. These climate shifts did not happen abruptly in human terms. They unfolded slowly, sometimes unevenly, but persistently enough to reshape the southern oceans in ways that likely made them less accessible to a species like Megalodon. One of the most significant developments involved the strengthening of Antarctic glaciation. Ice had begun forming on Antarctica well before the Miocene, but its extent fluctuated considerably. During warmer intervals, ice retreated toward the continental interior, leaving coastal areas more exposed and surrounding waters less intensely cold. As global temperatures gradually declined, especially from the late Miocene into the Pliocene, ice sheets expanded outward more consistently. This expansion increased surface reflectivity, known as albedo, which reinforced cooling by reflecting more solar radiation back into space. At the same time, ocean circulation patterns shifted. The Antarctic circumpolar current, already forming earlier, intensified as continental gateways widened fully and wind patterns stabilized. This powerful current effectively isolated Antarctic waters thermally, limiting the southward flow of warm equatorial water. Modern oceanography recognizes this current as one of the strongest on the planet, acting like a cold barrier encircling the continent. As it strengthened during the late Miocene and Pliocene, southern marine environments became progressively colder. Temperature declines influenced marine ecosystems directly. Plankton communities began shifting toward cold-adapted species. Fossil microplankton assemblages from southern sediment cores show increasing dominance of cold-water taxa over time. These changes at the base of the food web cascade upward, affecting fish distributions, marine mammal feeding grounds, and ultimately apex predators. Sea level changes accompanied cooling as well. Expanding ice sheets locked up significant volumes of water, causing global sea levels to fall. Lower sea levels reduce the extent of shallow continental shelf habitats, which are often the most productive marine zones. Shelf contraction would have reduced feeding areas for marine mammals and fish, indirectly limiting prey availability for large predators. Marine mammal evolution during this period also reflects changing conditions. Some whale lineages adapted successfully to colder waters, while others declined or shifted migration patterns. Fossil records indicate alterations in whale distribution consistent with expanding polar cooling. If Megalodon relied heavily on certain whale species as prey, shifts in whale migration routes would influence shark distribution as well. Ocean stratification increased with cooling. Stronger temperature differences between surface and deep water layers can limit vertical nutrient mixing. Reduced mixing often leads to lower surface productivity outside specific upwelling zones. Geological proxies suggest changes in nutrient distribution in southern oceans during late Miocene cooling phases, potentially affecting overall ecosystem productivity. Salinity patterns shifted alongside temperature. Increased ice formation removes fresh water from the ocean system, raising salinity in some regions, while meltwater pulses during glacial retreats temporarily lower it. These fluctuations influence ocean density gradients and circulation dynamics, adding further complexity to marine habitat stability. Wind systems evolve too. Strengthening circumpolar westerlies enhanced cold water isolation around Antarctica. These winds drive surface currents and influence ocean mixing. Climate models incorporating paleogeographic reconstructions consistently show increasing wind-driven circulation intensity during the Pliocene cooling trend. Tectonic factors continued influencing climate as well. Ongoing uplift of mountain ranges in various parts of the world altered atmospheric circulation patterns, contributing indirectly to global cooling. While not specific to Antarctica, these changes affected overall climate balance, reinforcing polar ice expansion. Chemical evidence preserved in marine sediments documents these transitions. Oxygen isotope ratios from deep-sea foraminifera show increasing global ice volume over time. Carbon isotope shifts reflect changes in ocean productivity and carbon cycling. Together, these chemical proxies provide a timeline for progressive cooling that overlaps with the later portion of Megalodon's existence. Marine ecosystem restructuring followed predictable patterns. Cold-adapted species expanded southward. Temperate and warm-adapted species either migrated toward lower latitudes or declined. Predator-prey relationships reorganized accordingly. Such ecological transitions rarely eliminate species instantly. but can reduce available habitat gradually. For a large apex predator requiring substantial caloric intake, even modest reductions in prey density can have significant consequences. Large sharks cannot easily subsist on sparse resources. As productive shelf habitats contracted and prey migration patterns shifted, southern regions likely became less attractive destinations. Competition dynamics may also have changed, so emerging predators, including certain toothed whale lineages capable of active predation, appear increasingly in late Miocene and Pliocene fossil records. These predators may have competed with Megalodon for overlapping prey resources, particularly in regions where prey abundance declined. Thermal tolerance limits eventually become critical. Even species capable of moderate temperature flexibility encounter physiological boundaries. Progressive cooling could push environmental conditions beyond what a warm-adapted predator could tolerate comfortably, especially for extended periods. Fossil distribution patterns reflect these changes. Earlier Miocene deposits show broader Megalodon geographic spread, including more southern occurrences. Later, Pliocene deposits increasingly concentrate in lower latitudes. While sampling bias always requires consideration, this pattern aligns with climate-driven habitat contraction. Changes in ocean chemistry accompanied cooling as well. Increased carbon dioxide solubility in colder water influences pH and carbonate availability. Such chemical shifts affect plankton species composition, which then affects entire food webs. These cascading effects further reshape marine ecosystems. Glacial cycles introduced additional variability. Periodic ice advances and retreats cause short-term environmental oscillations. Species capable of rapid adaptation might persist through such fluctuations, but long-term cooling trends often exert stronger influence on evolutionary outcomes. Extinction events rarely result from a single factor. For Megalodon, climate cooling likely interacted with prey evolution, competition, and habitat restructuring. Southern ocean cooling represents one component of a broader environmental shift affecting global marine ecosystems. Evidence from associated marine fossils reflects this transition. Cold-adapted whale species appear more frequently in later deposits. Some earlier temperate species decline. Fish assemblages shift toward cold-tolerant taxa. These patterns support climate-driven ecological change. Ocean gateway stabilization also contributed. Fully developed circumpolar circulation reduced the intermittent warm water incursions that earlier may have extended habitable conditions southward. Once that isolation became stable, southern marine environments maintained consistently colder conditions. Modern Antarctica illustrates the endpoint of this long process. Extensive ice sheets, persistent cold currents, and specialized cold-adapted ecosystems characterize the region today. The contrast with earlier Miocene conditions highlights how gradual climate shifts can fundamentally transform entire regions. Scientific interpretation remains cautious. While climate cooling provides a plausible explanation for reduced southern Megalodon presence, precise causal relationships remain complex. Multiple interacting factors likely influence the species' eventual extinction. Nevertheless, the overall pattern suggests that environmental conditions which once permitted occasional southern excursions gradually diminished. Warmer currents weakened, shelf habitats shrank, prey distribution shifted, and colder conditions became more persistent. These cumulative changes effectively narrowed the ecological window that might have allowed a large warm-adapted predator to venture toward Antarctic waters. With climate shifts framing the environmental constraints, the ongoing scientific conversation naturally includes differing interpretations of the available evidence. Not all researchers agree on how far south Megalodon ranged, or how significant southern habitats were, which leads into the broader discussion of scientific debate and the uncertainties inherent in reconstructing ancient ecosystems. As more pieces of evidence accumulate from fossil teeth to isotope chemistry, sediment layers, ocean current reconstructions, and associated marine fossils, it might seem as if the picture should become straightforward. Yet in science, especially when dealing with deep time and incomplete records, certainty rarely arrives in a clean final form. Instead, discussion continues, interpretations evolve, and skepticism plays a constructive role. The question of whether Megalodon truly ventured close to Antarctic waters is a good example of how scientific understanding develops through debate rather than immediate agreement. One reason for ongoing debate is the nature of the fossil record itself. Fossils are inherently selective. Preservation requires very specific conditions: rapid burial, low oxygen environments, minimal disturbance over millions of years, and favourable mineral chemistry. Many marine environments simply do not preserve remains well. Others remain inaccessible beneath deep ocean sediments, or in Antarctica's case, thick ice. Because of this uneven preservation, absence of fossils does not automatically mean absence of the organism, but neither does a small number of finds guarantee widespread presence. Some researchers therefore urge caution when interpreting southern megalodon teeth. They point out that isolated teeth, even when well preserved, represent limited data points across vast oceans and long time scales. Ocean currents, storms, and sediment transport can relocate remains. Determining whether a tooth reflects local habitat or post-mortem transport requires detailed contextual analysis, and not all fossil sites provide equally clear context. Dating uncertainty also contributes to debate. While radiometric techniques, biostratigraphy, and paleomagnetic analysis have improved precision, margins of error still exist. A tooth assigned to a particular climatic interval might actually belong to a slightly earlier or later phase. Since climate conditions shifted repeatedly during the Miocene and Pliocene, even modest dating uncertainty can affect habitat interpretations. Isotopic analysis, although powerful, has limitations too. Physiological factors complicate environmental readings. If Megalodon maintained elevated internal temperatures through regional endothermy, isotope ratios in teeth might reflect body chemistry more than surrounding seawater. Scientists attempt to correct for this, but assumptions remain. Skeptical researchers emphasize these physiological uncertainties when interpreting temperature tolerance. There is also discussion about ecological plausibility. Some scientists argue that Megalodon likely preferred warmer waters consistently, and that southern occurrences represent peripheral excursions rather than regular habitat use. This interpretation suggests occasional migration rather than sustained presence. Others propose broader ecological flexibility, citing fossil distribution and chemical evidence. Sampling bias represents another concern. Fossil collecting historically focused on accessible coastal regions with active research infrastructure. Southern ocean areas, particularly near Antarctica, remain undersampled due to logistical challenges. That uneven sampling can distort perceived distribution patterns. Some researchers suggest that future discoveries could significantly alter current understanding, either strengthening or weakening the southern range hypothesis. Comparisons with modern sharks generate mixed interpretations as well. Some scientists see strong parallels between Megalodon and great white sharks in terms of temperature tolerance and migration. Others caution against over-reliance on modern analogues, noting evolutionary differences in ecological contexts that may not translate directly. Competition with other predators introduces further complexity. Fossil evidence of large predatory toothed whales emerging during the late Miocene raises questions about ecological interactions. Some researchers argue that increasing competition may have restricted Megalodon's range, particularly in marginal environments like southern oceans. Others consider this factor secondary compared with climate change. Another area of debate involves the interpretation of associated marine fossils. While whale and fish remains found alongside Megalodon teeth suggest shared ecosystems, critics note that temporal overlap within sediment layers does not always imply direct ecological interaction. Fossil assemblages can accumulate over extended periods, potentially blending species that did not coexist simultaneously. climate modelling itself is not immune to scrutiny. Paleoclimate simulations depend on assumptions about atmospheric composition, continental configuration, ocean gateway depth, and many other variables. Different models sometimes produce slightly different temperature reconstructions for southern oceans during the Miocene. Researchers weigh these differences carefully before drawing ecological conclusions. Public perception sometimes complicates scientific discussion. Media portrayals often simplify findings into dramatic claims about prehistoric giants roaming polar seas. Scientists tend to respond by emphasizing nuance, probabilities, and uncertainty. This cautious communication can appear hesitant, but it reflects methodological rigor rather than lack of evidence. Peer review functions as a central mechanism in this process. New studies proposing expanded Megalodon range undergo detailed evaluation by other experts. Reviewers examine methodology, sample quality, statistical analysis, and interpretation logic. Constructive criticism often leads to refined conclusions rather than outright rejection. Interdisciplinary collaboration also shapes debate. Paleontologists, geochemists, oceanographers, climate modelers, and evolutionary biologists each contribute perspectives. Differences in disciplinary focus sometimes produce varying interpretations of the same evidence, but integration over time usually leads to more balanced understanding. Museum collections continue playing an unexpected role in ongoing debate. Specimens collected decades ago occasionally receive new analysis using modern techniques. Reinterpretation of existing fossils sometimes shifts scientific consensus gradually, without dramatic new discoveries. Technological advances add further layers: improved isotopic precision, better sediment core recovery, and enhanced imaging methods continuously refine data quality. Each improvement has potential to clarify previous ambiguities or raise new questions. Scientific skepticism in this context is not opposition for its own sake. It serves as quality control. Challenging assumptions helps prevent premature conclusions. When multiple independent lines of evidence converge despite scrutiny, confidence increases. Educational background and research focus can influence interpretation as well. Scientists specializing in marine predator ecology may emphasize biological plausibility, while geochemists may focus on chemical uncertainties. Balanced conclusions typically emerge through dialogue between these perspectives. Historical shifts in scientific opinion illustrate how understanding evolves. Early Megalodon research often assumed strictly tropical distribution. Later fossil discoveries expanded perceived range. Continued analysis may refine that picture further, without necessarily overturning earlier work completely. Funding priorities also affect research direction. Antarctic exploration requires significant logistical resources. Limited funding can slow data collection, prolonging uncertainty. As funding availability changes, research emphasis can shift accordingly. Despite ongoing debate, several points of broad agreement exist. Megalodon was globally distributed. Southern Hemisphere fossil evidence is credible. Miocene southern oceans were warmer than today. Marine mammal prey existed in those regions. Where disagreement persists is primarily about degree and frequency of southern presence. This measured uncertainty reflects the complexity of reconstructing ancient ecosystems. Unlike modern ecological studies, direct observation is impossible. Scientists rely on indirect evidence, modelling, and comparative analysis. Absolute certainty remains rare. As research continues, discussion often moves toward understanding the limits of the fossil record itself. Recognizing what fossils cannot tell us can be as important as interpreting what they can. That perspective naturally leads into the question of how absence of evidence should be interpreted in paleontology, particularly in challenging environments like southern polar regions. As scientific discussions continue around southern fossil discoveries, an important concept gradually enters the conversation, one that often sounds simple, but becomes surprisingly complex when applied to deep-time research. That concept is the difference between absence of evidence and evidence of absence. It appears frequently in paleontology, especially when investigating environments where fossil preservation is uneven or where exploration remains limited. The question is not merely whether something has been found, but whether it reasonably could have been found given the conditions under which fossils form, survive, and are eventually discovered. Fossilization itself is a rare process. Most organisms, marine or terrestrial, leave no trace at all. Soft tissues decompose quickly, and even hard tissues require specific conditions to survive. Rapid burial in sediment, low oxygen environments, minimal scavenging, and stable geological conditions all improve preservation chances. Without those factors, biological remains simply disappear. This basic reality means the fossil record represents a tiny fraction of past life rather than a complete archive. Marine environments add additional complications. Ocean floors are dynamic. Sediments shift. Tectonic activity recycles crust into the mantle, and chemical dissolution can destroy mineralized remains. Deep ocean sediments, where preservation might occur, often remain inaccessible without specialized drilling equipment. Antarctica amplifies these challenges further because thick ice sheets cover large portions of potentially fossil-bearing strata. Ice coverage does more than block access. It also influences erosion patterns, sediment deposition, and exposure cycles. Some fossil-bearing layers may remain buried indefinitely beneath ice sheets. Others might erode before researchers ever reach them. These processes create large gaps in accessible data. Consequently, lack of Megalodon fossils directly on the Antarctic continent does not automatically confirm the species never entered surrounding waters. Sampling bias plays a significant role in paleontology. Regions with active research institutions, favourable climates, and accessible geology produce more fossil discoveries. Tropical and temperate coastal areas have historically received more attention than remote polar environments. Southern Ocean exploration remains logistically expensive and weather-dependent, limiting systematic fossil searches. Temporal bias also exists. Certain geological periods preserve fossils more effectively than others. Changes in sea level, sedimentation rates, and ocean chemistry affect preservation potential. Some intervals leave abundant records, others leave almost none. Megalodon's existence spanned multiple climate phases, and preservation conditions varied across those phases. Transport processes complicate interpretation as well. Ocean currents, storms, and sediment slumping can move remains after death. Distinguishing locally deposited fossils from transported ones requires careful sedimentological analysis. Even when transport occurs, it usually leaves identifiable signs such as abrasion, fragmentation, or mixed assemblages, but interpretation still involves uncertainty. Geological recycling further reduces available evidence. Oceanic crust eventually subducts beneath continental plates. Sediments containing fossils can be destroyed during this process. Over tens of millions of years, significant portions of ancient seafloor have disappeared entirely, along with any biological evidence they once contained. Preservation chemistry introduces additional variability. Calcium carbonate dissolves under certain ocean conditions, particularly at greater depths where pressure and acidity increase. This carbonate compensation depth fluctuates over geological time. If fossil remains formed below this depth during certain periods, they might dissolve before fossilization completes. Even when fossils survive, discovery depends on exposure. Erosion, tectonic uplift, or human excavation must bring fossil-bearing layers within reach. Many marine sediments remain buried beneath younger deposits. Without drilling or natural exposure, they remain unseen. Analytical techniques also influence what counts as evidence. Earlier generations of paleontologists relied primarily on visible morphology. Modern researchers use chemical analysis, isotopic data, microfossils, and remote sensing. Specimens once considered uninformative may now yield valuable data, meaning absence of earlier evidence sometimes reflects technological limitations rather than true absence. interpretation bias can occur unconsciously. Researchers may expect certain species only in certain environments based on modern analogues. Such expectations influence where they look and how they interpret ambiguous finds. Recognition of this bias has encouraged broader search strategies in recent decades. Statistical approaches attempt to address these uncertainties. Paleontologists use probabilistic models to estimate species distribution based on known fossil occurrences and sampling intensity. These models rarely produce absolute answers but help gauge likelihoods. For Megalodon, such modelling generally supports broad global distribution, with potential peripheral extensions rather than strict tropical confinement. Museum collections often contain overlooked specimens. Fossils collected decades ago sometimes lacked precise dating or contextual information. Re-examining these collections with modern methods occasionally reveals new environmental insights. This retrospective analysis can partially compensate for limited field access. Public interpretation sometimes oversimplifies absence of evidence into definitive statements. Scientific communication tends to emphasize uncertainty more explicitly. Phrases like "no confirmed evidence" reflect methodological caution. Rather than denial of possibility, interdisciplinary data integration helps address gaps. Climate models, sediment chemistry, biological analogues, and geological reconstructions combine to provide context even when direct fossils are scarce. Converging indirect evidence can strengthen hypotheses while acknowledging missing pieces. Antarctica presents a particularly instructive example. Much of its geological history remains buried under kilometres of ice. Limited coastal exposures provide glimpses, but vast interior regions remain unexplored. Marine sediments offshore require specialised drilling campaigns. Consequently, the fossil record there remains fragmentary. Scientific consensus evolves gradually as evidence accumulates. Early assumptions about strict tropical Megalodon distribution softened as southern hemisphere fossils appeared. Future discoveries could refine this picture further in either direction. Flexibility in interpretation reflects responsible scientific practice. Environmental reconstructions rely on multiple proxy indicators. When independent proxies align, confidence increases even if direct fossils remain limited. Temperature proxies, associated fauna, and oceanographic modelling collectively inform understanding. Educational outreach sometimes emphasises dramatic certainty for accessibility, but research literature maintains more nuanced positions. Distinguishing between popular presentation and scientific analysis helps clarify debates. Philosophically, the absence of evidence issue highlights limits of empirical knowledge. Science operates through available data, always subject to revision. Recognizing these limits does not weaken conclusions, it clarifies their scope. In the specific case of Megalodon and southern oceans, absence of abundant Antarctic fossils suggests caution, but does not invalidate broader ecological plausibility supported by indirect evidence. Balanced interpretation acknowledges both possibilities and uncertainties. Technological advances continue reducing some gaps. Improved drilling technology, remote sensing, and analytical chemistry increase the likelihood of future discoveries. Antarctic research infrastructure continues expanding gradually, offering new opportunities. Ultimately, understanding what absence of evidence means encourages careful, measured conclusions. It prevents overstating claims while keeping inquiry open. That mindset supports continued exploration rather than premature closure. As research tools evolve, new technologies increasingly contribute to uncovering hidden clues. High-resolution imaging, geochemical analysis, and deep-sea exploration methods continue expanding what scientists can detect, even in challenging environments, shaping the next phase of investigation into ancient marine ecosystems. As the discussion moves from what fossils show to what might still remain hidden, the role of technology becomes increasingly important. For a long time, paleontology depended mostly on visible discoveries. someone found a fossil exposed in rock, collected it, studied its shape, and compared it with known species. That approach still matters, but modern research adds layers of investigation that go far beyond what the eye alone can detect. Particularly when studying remote environments like southern oceans near Antarctica, technology often becomes the main way scientists gather new information without needing constant direct access to every site. One of the most influential developments involves high-resolution imaging techniques. Computed tomography scanning, often simply called CT scanning, allows researchers to examine the internal structure of fossils without cutting them open. A Megalodon tooth, for example, might look uniform externally, but CT imaging reveals growth layers, internal density variations, and sometimes microscopic cracks that provide clues about how the tooth formed and how it fossilized. These internal structures can suggest environmental conditions, feeding behavior, and even aspects of the shark's growth rate. Synchrotron imaging pushes this even further. Using intense beams of radiation generated in specialized facilities, scientists can map chemical elements inside fossils at extremely fine scales. This technique helps distinguish original biological signals from later mineral contamination. For Megalodon research, such analysis can clarify whether isotopic temperature readings truly reflect ancient seawater conditions, or whether fossilization processes altered the chemistry afterward. Laser ablation mass spectrometry represents another important advancement. This method involves vaporizing microscopic portions of a fossil surface with a laser and analyzing the resulting particles chemically. Because the laser can target specific growth bands within a tooth, researchers can sometimes reconstruct environmental changes experienced by an individual shark over time. That level of detail was impossible only a few decades ago. Deep-sea drilling technology has also transformed marine paleontology. Specialized drilling vessels extract sediment cores from ocean floors thousands of meters deep. These cores contain layered records of microfossils, chemical proxies, and sediment characteristics spanning millions of years. Southern Ocean drilling projects have yielded temperature records, plankton assemblages, and chemical data that help reconstruct conditions during the Miocene and Pliocene, providing context for interpreting Megalodon distribution. Remote sensing plays a complementary role. Satellite observations track modern ocean currents, temperature patterns, and productivity zones. While these observations reflect current conditions, they help validate climate models used to reconstruct ancient oceans. By understanding how present currents behave, scientists improve simulations of past circulation patterns. Seismic reflection surveying allows researchers to map buried sediment layers without excavation. Sound waves transmitted through the seabed reflect differently depending on sediment density and composition. Interpreting these reflections produces detailed subsurface images. Such surveys identify ancient continental shelves, submerged valleys, and sediment basins where fossils may exist even if they remain inaccessible. Autonomous underwater vehicles, often abbreviated but increasingly familiar in marine research, extend exploration into areas too deep or hazardous for divers. Equipped with cameras, sonar, and sampling tools, these vehicles map seafloor topography, identify sediment deposits, and occasionally recover samples. Southern Ocean missions using these vehicles have expanded geological knowledge significantly. Advances in geochemical laboratory equipment have improved analytical precision. Mass spectrometers now measure isotope ratios with greater accuracy than earlier generations allowed. That precision reduces uncertainty when reconstructing ancient water temperatures or dietary patterns from fossil teeth. Machine learning techniques are beginning to assist fossil identification and environmental modeling. Algorithms trained on large fossil data sets can recognize patterns humans might overlook. These systems help correlate fossil occurrences with environmental proxies, suggesting new hypotheses for testing. Digital fossil databases also facilitate collaboration. Researchers across continents can access detailed images, chemical data, and contextual information from previously collected specimens. This shared access accelerates comparative studies without requiring constant physical specimen transport. Microscopic analysis techniques have improved too. Scanning electron microscopy reveals surface features on fossils at nanometer scales. Such detail helps differentiate wear patterns caused by feeding from those caused by sediment abrasion or fossilization processes. Paleogenomic approaches, although limited for very old marine fossils, are advancing gradually. While Megalodon lived too long ago for DNA preservation under most conditions, associated younger marine fossils sometimes yield genetic material. These data inform evolutionary relationships and environmental adaptation patterns indirectly relevant to broader ecosystem reconstructions. Oceanographic sensor networks provide continuous modern data on temperature, salinity, nutrient levels, and current behavior. These data refine climate models projecting backward into geological time. Better modern baselines improve paleoclimate simulation reliability. Chemical mapping of sediment cores now includes multiple isotope systems simultaneously. Oxygen, carbon, strontium, and other isotopes together provide more comprehensive environmental reconstructions than any single proxy alone. Three-dimensional fossil modelling has improved educational and research access. High-resolution scans create digital replicas of rare specimens. Researchers can analyse morphology remotely, and educational outreach benefits without risking damage to fragile originals. Polar research infrastructure has expanded gradually as well. Ice-capable research vessels, improved satellite communication, and advanced weather forecasting increase fieldwork safety and feasibility. While Antarctic research remains challenging, technological support continues improving. Climate modelling software has become more sophisticated, incorporating detailed paleogeography, atmospheric chemistry, and ocean physics. These models simulate ancient environmental conditions with increasing resolution. Their outputs help contextualize fossil findings. Data integration platforms now allow simultaneous visualization of fossil distributions, climate proxies, ocean current simulations, and geological maps. This integrated perspective helps identify correlations that might otherwise remain unnoticed. Portable analytical equipment allows preliminary testing in field conditions. Handheld spectrometers can assess mineral composition immediately after fossil discovery, guiding further sampling decisions. Radiometric dating precision continues improving through refined calibration curves and analytical methods. More accurate age estimates help correlate fossil occurrences with specific climatic intervals. Public engagement technology also contributes indirectly. Virtual fieldwork simulations, digital archives, and interactive models broaden awareness, sometimes leading to citizen science contributions or renewed interest in underexplored regions. Despite these advances, technology does not eliminate uncertainty. Analytical results still require interpretation. Models depend on assumptions. Fossil records remain incomplete. Technology expands capability but does not guarantee definitive answers. Still, each technological improvement increases the resolution of the ancient environmental picture. Details once invisible become measurable. Patterns once speculative gain supporting data. Southern Ocean research particularly benefits because direct field access remains limited. As tools continue evolving, new discoveries become increasingly likely. Previously collected specimens may yield additional information under improved analysis. Future Antarctic drilling or remote exploration could uncover sediments, preserving clearer evidence of prehistoric marine ecosystems. With technology gradually illuminating hidden clues, the broader question returns to visualizing what those ancient southern oceans actually looked like. Combining fossil evidence, climate modeling, and technological insights allows researchers to reconstruct past environments more vividly, offering a clearer sense of how different Antarctica's surrounding seas once were compared with today. Once all those strands begin to come together, the fossil chemistry, the associated marine species, The geological reconstructions, the ocean current models, and the increasingly precise technological insights, a clearer picture slowly forms of what the southern oceans might actually have looked like millions of years ago. Not a frozen, silent expanse dominated by ice shelves as we know today, but a very different marine environment, still challenging in some respects, yet far more biologically active and thermally moderate than modern Antarctica suggests. Reconstructing that past ocean is not an exercise in imagination alone. It relies on accumulated physical evidence, climate modelling, and comparisons with modern ecosystems that function under similar conditions. The first noticeable difference would have been temperature. While still cooler than equatorial waters, southern seas during certain Miocene intervals were likely temperate rather than polar in the modern sense. Oxygen isotope data from marine sediments and fossil shells consistently indicate water temperatures significantly higher than those surrounding Antarctica today. Seasonal variation existed, but the extreme year-round cold conditions familiar now had not yet fully developed. This warmer baseline would have influenced nearly every aspect of marine life. Plankton productivity appears to have been strong, supported by nutrient upwelling and seasonal sunlight cycles. Diatom-rich sediment layers suggest repeated plankton blooms, forming the energetic base for complex food webs. These blooms would not necessarily have produced constant abundance, but seasonal peaks could sustain large populations of fish and marine mammals. Visibility in those ancient waters likely varied. Productive plankton blooms often reduce water clarity, while calmer periods allow clearer conditions. Such fluctuations resemble modern temperate coastal seas more than the often icy, low-visibility waters around Antarctica today. For predators relying on multiple sensory systems, including electroreception and vibration detection, these conditions would remain workable. Marine mammals would have been a prominent feature. Fossil whale remains in southern hemisphere Miocene deposits indicate feeding grounds extending into higher latitudes than modern breeding grounds. Baleen whales feeding on plankton, toothed whales hunting fish and squid, and pinnipeds occupying coastal haul-out sites together create a dynamic ecosystem. Such diversity implies sustained biological productivity, rather than isolated ecological pockets. Fish populations likely included both schooling species and larger predatory fish. Otolith fossils and skeletal remains suggest varied communities adapted to moderate temperatures. Schooling fish often respond quickly to plankton blooms, concentrating biomass in ways that attract higher predators. This dynamic appears consistently in both modern temperate oceans and fossil reconstructions of Miocene southern seas. Coastal environments would also have differed markedly. Instead of extensive ice shelves reaching the sea, some coastlines likely supported vegetated areas, river systems, and sediment input from terrestrial erosion. Fossil pollen in marine sediments indicates nearby land vegetation during certain intervals. These terrestrial inputs supply nutrients to coastal waters, enhancing productivity. Sea ice, if present at all during warmer intervals, would have been seasonal and less extensive. Seasonal ice cover affects marine ecosystems differently from permanent ice sheets. It influences light penetration, nutrient mixing, and habitat accessibility without completely isolating marine environments year-round. Ocean currents played a central role in shaping this environment. Warm surface currents extending southward along continental margins would moderate temperatures and transport nutrients. These currents also guide migratory marine species. Climate models consistently suggest that before full development of the modern Antarctic circumpolar current, Southern Ocean circulation allowed greater mixing with warmer mid-latitude waters. Sound propagation underwater would also differ in warmer seas. Temperature gradients influence acoustic transmission. Marine mammals relying on echolocation and communication might experience different acoustic conditions compared with modern Antarctic waters. While subtle, such differences affect predator-prey interactions. Seafloor habitats contributed additional ecological complexity. Benthic communities, including mollusks, crustaceans, echinoderms, and burrowing organisms, appear in southern fossil assemblages. These communities recycle organic matter, sinking from surface waters, maintaining nutrient cycling essential for long-term ecosystem stability. Kelp-like macroalgae may have existed along some temperate southern coastlines, though direct fossil evidence is limited. Sediment chemistry and associated fauna suggest the possibility of vegetated coastal zones supporting juvenile fish populations. Such habitats often serve as nursery grounds in modern temperate seas. Atmospheric conditions would have differed as well. Warmer global climates reduce extreme temperature gradients between equator and poles. That moderation influences storm patterns, wind strength, and precipitation. These atmospheric factors indirectly shape marine productivity and ocean circulation. Daylight cycles near polar regions remain extreme regardless of temperature. Extended summer daylight promotes plankton blooms, while winter darkness reduces productivity. Ancient southern ecosystems likely followed similar seasonal rhythms, though moderated by warmer baseline temperatures. Predator presence, including large sharks like Megalodon, would fit naturally into such ecosystems if prey availability remained sufficient. The image is not of a permanently polar predator population, but rather a dynamic marine environment capable of supporting seasonal or occasional large predator visits. Geological shoreline changes would also affect habitat distribution. Higher sea levels during warmer intervals submerged continental shelves extensively, creating shallow, productive seas. These expanded shelf environments serve as key feeding grounds for marine mammals and fish. Sediment composition supports these reconstructions. Marine sediments rich in organic material, microfossils and nutrient indicators appear repeatedly in southern Miocene deposits. These features align with productive temperate marine ecosystems rather than cold, nutrient-limited polar seas. Modern analogues help illustrate possibilities. Regions like the southern tip of South America or parts of New Zealand today experience temperate marine climates with strong productivity. While not identical to ancient Antarctic conditions, they offer reasonable comparisons for reconstructing ecosystem structure. Climate variability still existed, of course. Even during warmer intervals, cooler phases occurred. Marine ecosystems adapted accordingly, shifting species distribution, productivity patterns, and migration routes. Megalodon, if present in southern waters, likely followed these shifting ecological signals rather than maintaining permanent residence. Scientific caution remains important. Reconstructions integrate multiple indirect data sources. Each source carries uncertainty. The combined picture gains strength through consistency rather than any single definitive observation. Technological advances continue refining these reconstructions. Improved sediment cores, isotopic precision, and climate modelling steadily enhance resolution. Future discoveries may clarify details further, particularly in underexplored southern ocean regions. Understanding these ancient polar oceans helps contextualize broader evolutionary patterns. Species adaptation, migration, and extinction often reflect environmental change rather than isolated biological factors. Megalodon's potential southern presence fits within this larger ecological narrative. As attention expands from specific ecosystems to broader evolutionary trends, the discussion naturally connects with how large marine predators evolve, adapt, and eventually disappear in response to environmental change. That wider perspective helps place Megalodon's story within the ongoing history of ocean giants across geological time. When the view widens beyond a single species and its possible southern range, the story starts to include a longer pattern, one that stretches across many millions of years of ocean history. Megalodon becomes part of a broader sequence of large marine animals that rose to ecological prominence, adapted to shifting conditions, and eventually disappeared as those conditions changed again. Looking at that broader story helps place the discussion about Antarctic waters in context, because it shows how often large marine predators expand or contract their ranges in response to environmental pressures rather than remaining fixed in one geographic zone. Large body size in the oceans appears repeatedly throughout evolutionary history. It offers advantages. Bigger animals travel farther with less relative energy expenditure, maintain more stable internal temperatures, and often occupy top trophic levels where competition can be lower. Marine mammals, large sharks, marine reptiles in earlier eras, and even giant fish demonstrate this recurring evolutionary trend. Each group, however, emerged under specific environmental conditions that later shifted. Before Megalodon, earlier marine reptiles such as mosasaurs and plesiosaurs dominated ocean predator roles during the late Mesozoic era. Their extinction at the end of the Cretaceous cleared ecological space that later fish and shark lineages filled. Sharks, already present for hundreds of millions of years, diversified into new niches. By the time Megalodon appeared during the Miocene, sharks had long experience adapting to changing marine environments. Megalodon's rise coincided with an expansion of marine mammals, particularly whales. This timing is significant. Apex predators often track the abundance of large prey species. As baleen whales diversified and increased in size, a predator capable of exploiting that resource gained ecological advantage. Fossil bite marks on whale bones support this predator-prey relationship, indicating active ecological interaction rather than coincidence. Body size trends among marine mammals also increased during this period. Larger whales appeared gradually, likely in response to changing feeding strategies, ocean productivity patterns, and predator pressures. Predator-prey escalation sometimes leads to evolutionary size increases on both sides, a pattern seen in various ecosystems. Ocean giants do not exist in isolation. Their success depends on stable food webs, suitable climate conditions, and accessible migration corridors. When any of these factors shift significantly, large predators often respond through range changes, dietary adaptation, or eventual decline. Megalodon's later history aligns with such patterns. Climate cooling during the late Miocene and Pliocene affected not only Megalodon, but many marine species. Some whale lineages adapted successfully to colder waters, developing thick blubber layers and migration strategies that took advantage of polar productivity. Sharks, relying more heavily on warmer conditions, may have faced increasing constraints. Competition also plays a role in these broader patterns. Emerging predatory toothed whales, including early relatives of modern sperm whales and orcas, occupied ecological niches overlapping partly with large sharks. While direct competition evidence remains limited, overlapping prey preferences suggest possible ecological pressure. Evolutionary turnover among apex predators is common. Marine ecosystems repeatedly replace dominant predators over geological time. Environmental shifts, prey evolution, and competition all contribute. Megalodon's extinction around 3.6 million years ago fits within this broader pattern rather than standing as an isolated event. Range flexibility often determines survival during environmental transitions. Species capable of adapting to new temperature ranges, prey distributions, or habitats tend to persist longer. Evidence suggests Megalodon exhibited some flexibility, but perhaps not enough to overcome the combined effects of cooling oceans, shifting prey, and evolving competitors. Looking across modern oceans reinforces this pattern. Large whales today undertake extensive migrations linked to productivity cycles. Large sharks follow temperature gradients and prey movements. These behaviours reflect ecological adaptability rather than fixed geographic preference. Gigantism itself introduces both advantages and vulnerabilities. Large size improves energy efficiency and movement and thermal stability, but it also increases absolute food requirements. When ecosystems contract or prey availability declines, large predators face disproportionate challenges. Ocean productivity fluctuates over geological time. Nutrient cycles, continental positioning, atmospheric composition, and ocean circulation all influence primary productivity. These baseline changes cascade upward through food webs, affecting apex predator viability. Extinction rarely results from a single cause. Megalodon likely faced a combination of cooling climates, sea level changes reducing shallow habitats, evolving prey distributions, and competition from emerging marine predators. Each factor alone might be manageable, but together they create cumulative pressure. Studying these patterns helps inform modern marine conservation. Current climate change, overfishing, and habitat alteration affect large marine species today. Historical examples illustrate how environmental change can reshape ocean ecosystems over relatively short geological intervals. Fossil evidence of repeated apex predator turnover underscores ecosystem resilience as well. While individual species disappear, ecological roles often persist, filled by new organisms adapting to current conditions. After Megalodon's extinction, other large predators continued occupying upper trophic levels. Marine biodiversity overall tends to recover over long timescales, following major environmental shifts. This resilience does not reduce the significance of extinctions, but provides perspective on ecological continuity. Technological advances continue revealing new details about ancient ocean giants. Isotopic studies, climate modelling, and fossil discoveries refine understanding continuously. Interpretations evolve gradually rather than changing abruptly. Public fascination with large extinct predators reflects broader human interest in scale, adaptation, and environmental change. These species provide accessible entry points for discussing complex ecological processes. Educational outreach increasingly emphasizes ecological context rather than isolated species narratives. Understanding how Megalodon fit into its environment offers more insight than focusing solely on size or dramatic imagery. Interdisciplinary research strengthens these broader interpretations. Paleontology, oceanography, climate science, evolutionary biology, and geochemistry each contribute pieces of the puzzle. Integrated perspectives produce more robust conclusions. Antarctic connections fit naturally within this broader story. Large marine predators historically expanded into regions when environmental conditions permitted. Later climate cooling restricted those ranges. Megalodon's possible southern excursions align with this general pattern, rather than representing an unusual anomaly. Modern climate trends remind researchers that ocean conditions continue evolving. Studying past transitions provides valuable analogues, though not direct predictions, for future ecological responses. Scientific humility remains important in this field. Fossil records remain incomplete, models imperfect, and interpretations subject to revision. Continued research gradually refines understanding without necessarily producing final answers. This broader evolutionary perspective leads naturally toward reflection on what remains unknown. Despite extensive research, significant uncertainties persist about Megalodon's precise range, behavior, and ecological interactions. Acknowledging those uncertainties allows discussion to close not with finality, but with ongoing curiosity about what future discoveries might reveal beneath Southern Ocean sediments and Antarctic ice. As the different strands of evidence settle into place, the picture that forms is not one of certainty carved into stone, but one of gradual understanding built from many small pieces. Fossil teeth, sediment chemistry, ocean current reconstructions, associated marine species, climate records, and technological advances all contribute parts of the story. None of them alone prove that Megalodon regularly swam near Antarctic waters, yet together they make the idea scientifically plausible during certain intervals when conditions were warmer and marine ecosystems extended farther south than they do today. That distinction between possibility and certainty is central to how paleontology works. The past rarely leaves complete documentation, so reconstruction depends on converging lines of evidence rather than single decisive discoveries. The Antarctic region itself represents one of the most challenging environments for fossil recovery. Thick ice sheets cover vast areas, limiting direct geological exposure. Offshore sediments remain difficult to access without specialized drilling programs. Weather conditions restrict research seasons. These logistical realities explain why southern fossil evidence accumulates slowly. Each new discovery, even a single tooth or sediment core sample, adds incremental detail to a much larger environmental reconstruction. Understanding ancient Antarctic-adjacent oceans also requires stepping outside modern assumptions. Today the region is associated with persistent cold, seasonal darkness, and extensive ice cover. Millions of years ago, especially during warmer phases of the Miocene, those conditions were less extreme. Ocean circulation allowed more heat transport southward. Marine productivity supported diverse ecosystems. Coastal habitats existed where ice now dominates. Recognizing that long-term environmental variability helps make sense of how large marine predators could occasionally expand their range. Large marine animals often respond strongly to prey distribution. Fossil evidence consistently shows marine mammals present in southern hemisphere temperate waters during Megalodon's time. Baleen whales, early pinnipeds, and diverse fish populations formed complex food webs. Apex predators typically follow such resources rather than remaining confined to narrow climatic zones. Modern shark migration studies support this principle. Temperature tolerance combined with prey tracking often shapes distribution patterns. Isotopic analysis of Megalodon teeth reinforces that ecological flexibility. Chemical signatures indicating cooler water formation environments appear in several southern hemisphere fossil sites. These readings do not indicate permanent cold water adaptation, but they suggest the species could tolerate a wider temperature range than once assumed. When interpreted alongside geological and ecological data, the possibility of seasonal southern excursions becomes increasingly reasonable. Geological context strengthens that interpretation. Continental shelf expansion during higher sea level phases created productive shallow marine environments. Ocean gateways allowed varying degrees of warm water circulation towards southern latitudes before full development of the modern Antarctic circumpolar current. Sedimentary evidence indicates sustained marine productivity in regions that today lie near cold polar waters. Climate cooling eventually changed those conditions. Expansion of Antarctic ice sheets, strengthening circumpolar currents, shifting prey distributions, and reduced shelf habitat all contributed to environmental restructuring. Megalodon's extinction roughly coincides with intensified global cooling and ecological reorganization. While multiple factors likely contributed, climate-driven habitat change appears central. Scientific debate continues because uncertainty remains inherent. Fossil preservation is uneven. Sampling remains incomplete. Analytical techniques continue improving. Skepticism ensures interpretations remain grounded in evidence rather than speculation. This ongoing discussion reflects normal scientific practice rather than disagreement about fundamental principles. Technological advances steadily improve resolution. High-precision isotope analysis, deep-sea drilling, remote sensing, and advanced imaging methods continue uncovering previously inaccessible information. Museum collections collected decades ago sometimes yield new insights when reanalyzed with modern tools. Antarctic research infrastructure continues expanding gradually, increasing opportunities for future discoveries. The broader evolutionary context also matters. Large marine predators have repeatedly expanded and contracted their ranges over geological time in response to environmental change. Megalodon fits within that long pattern rather than standing apart from it. Earlier marine reptiles dominated oceans before sharks rose to prominence. Later marine mammals assumed some apex roles after Megalodon disappeared. Ocean ecosystems remain dynamic. Modern marine biology benefits from understanding these historical patterns. Climate change, shifting ocean currents, and evolving prey distributions continue affecting large marine species today. Past examples illustrate how environmental transitions influence predator distribution, migration, and survival. These analogues provide perspective rather than direct prediction, but they remain informative. Public fascination with Megalodon often focuses on size alone, yet its ecological role offers deeper insight. As an apex predator, it reflects the health and structure of ancient marine ecosystems. Where Megalodon existed, productive food webs likely existed as well. Where conditions changed, its range responded accordingly. Antarctica's geological history continues unfolding slowly as new research accumulates. Ice cores reveal atmospheric conditions. Sediment cores record ocean chemistry. Fossils provide biological context. Integrated analysis gradually refines environmental reconstructions. Each dataset contributes another piece rather than providing final answers. The absence of extensive Antarctic megalodon fossils should therefore be interpreted carefully. Preservation challenges, limited exploration, and geological recycling reduce available evidence. Absence of abundant fossils does not automatically mean absence of the species, but it does encourage cautious interpretation. Balanced conclusions remain essential. Interdisciplinary collaboration increasingly defines this research. Paleontologists, geochemists, climate scientists, oceanographers, and evolutionary biologists contribute complementary expertise. Combined perspectives produce more robust environmental reconstructions than any single discipline could achieve alone. Educational outreach continues emphasizing these complexities. Instead of presenting prehistoric oceans as static backdrops for dramatic predators, modern interpretation focuses on dynamic ecosystems shaped by climate, geology, and biological interaction. That perspective helps explain why large predators appear where they do and why they eventually disappear. Technological development remains ongoing. Improved drilling capabilities, enhanced analytical precision, and expanded Antarctic research programs will likely provide additional data over time. New discoveries may confirm current interpretations, refine them, or introduce entirely new considerations. Scientific understanding evolves gradually. Southern ocean ecosystems today still display remarkable productivity despite cold conditions. Seasonal plankton blooms support whales, seals, fish, and birds. While modern conditions differ significantly from Miocene environments, they demonstrate the ecological importance of polar-adjacent marine systems. Historical reconstructions suggest that earlier, warmer phases amplified this productivity. Ocean circulation continues influencing global climate strongly. The Antarctic circumpolar current now isolates the continent thermally. Its development marked a major climatic turning point. Understanding its historical formation helps explain broader planetary climate trends, not just marine predator distribution. Megafaunal marine species remain sensitive indicators of environmental change. Their large energy requirements make them responsive to shifts in prey availability and habitat conditions. Megalodon's history reflects that sensitivity clearly. Expansion during favourable conditions and contraction during cooling phases align with ecological expectations. Museum archives continue offering opportunities for new insight. Fossils collected in earlier decades sometimes lacked precise contextual data or advanced chemical analysis. Revisiting those specimens with modern techniques often reveals additional environmental information. The fossil record remains active rather than static. Future Antarctic exploration may uncover additional fossil-bearing sediments currently hidden beneath ice or deep offshore deposits. Technological advances in drilling and remote exploration make such discoveries increasingly feasible, though still challenging. Scientific communication emphasizes probability rather than certainty in these reconstructions. Multiple independent evidence streams supporting similar conclusions increase confidence, but absolute confirmation remains rare in deep-time studies. This probabilistic approach reflects methodological rigor. Large prehistoric marine predators provide useful case studies for ecological resilience and vulnerability. Their responses to climate change illustrate broader biological principles. Studying those patterns contributes to understanding both past and present ocean ecosystems. As the accumulated evidence continues to expand, the Southern Ocean story remains open rather than finished. Each new fossil find, improved climate model, or refined chemical analysis adds another layer. The picture grows clearer gradually, though never completely final. Antarctica itself continues evolving geologically. Ice sheets advance and retreat on long timescales. Ocean currents shift subtly. Marine ecosystems adapt accordingly. The processes shaping that region today are part of the same long planetary dynamics that influenced Megalodon's world. Quiet persistence defines this kind of research. Progress rarely arrives dramatically. Instead, it accumulates through careful observation, repeated testing, and gradual refinement. The story of Megalodon and Southern Oceans reflects that steady scientific rhythm. And so the idea remains in motion rather than settled. Evidence continues to surface slowly, sometimes from unexpected places, sometimes from old specimens examined in new ways. Beneath Antarctic ice, within deep marine sediments, and inside fossil collections already gathered, further clues may still wait, adding detail piece by piece as understanding keeps moving forward.